And we are now recording. Let's get the slideshow set up from the current slide. Okay. And this is the slide we left off with last time. And I think we discussed this slide in pretty decent detail, so I don't think there's anything new here. Did either of you have a question on this slide? This is really getting into quantum mechanics. I know y'all are auto mechanics, but this is a different kind. Okay. If there are no questions, let's see. You know, that's not the slide. Yeah, we've already done this slide too. For some reason, the slides got off. Okay. There are the 3 rules of Bohr's theory. We did that one. Okay. Here's where we are. This is where we pick up today. All right. And here comes Thomas. Let me get him in before we proceed. So far, all Y chromosomes, no X chromosomes yet. That's sort of the story of my life. What have you done with them, folks? I think that's right there. Okay. Welcome, Thomas. For some reason, I'm only seeing one person at a time now. So yeah, we've still got 3 guys here, no gals, nobody in the waiting room. Okay, now we talked about this last time. Or first, any questions? Okay, wait, here comes some more. Now Amia breaks the string here. Whoa, my cords are getting all tangled up and stuff. Amia is here. All right, we got 3 in a row right in the middle of the class, 1 near the beginning and nobody at the end. So welcome, Amia. Okay, I think we'll let a few more people get here before I make announcements, because I want most of the people to be able to hear them without me repeating them every time someone else comes in. So here's where we were last time. The quantum theory of the atom. And these we talked about. This formula here is the Balmer equation or Balmer formula. Okay. Now, let me give you a few little things, ways in which quantum mechanics differs from classical mechanics. I'm not going to go into the full spiel. That probably would take a couple of courses, but let's just do a little bit. Okay. Now, first, in classical mechanics, you could reach a 0 energy level. You could reach a 0 on anything. Okay. Not so in quantum mechanics. In quantum mechanics, your lowest energy state is called, oh, here is Shay. Now, I think Shay may be Sharonica, because I don't think she's been here yet, so that's why I don't recognize Shay. Let me make sure of that. Shay, oh, you're not connected to a microphone yet. Needing to find out who Shay is. Okay, I still see no microphone for Shay. Sorry folks, we'll just wait until we get some communications with Shay. Here we go. Nope, yeah. Shay, is this Sharonica or who?
It's Sharonica.
Okay, good. I didn't know, I didn't recognize Shay. All right, well, welcome to the class. And what do you go by? Do you go by Shay or do you go by Sharonica?
Both of them. It don't really matter.
Okay, which would you prefer? I mean, this is next to the last day of class, so you choose. Huh?
You can call me
Shay?
Shay.
Okay. All right. Now, since this is your first day in the class, Do you need any kind of a review of the Blackboard and where to find things and stuff like that?
No. Well, I did have trouble with like submitting stuff.
Right,
I know that we have 2 labs in each week, but I was only submitting one at a time,
right.
and so now I can't submit the rest of them because I have nowhere to.
Okay. All right. Now that okay. Let me let's go back, folks. Now, y'all have heard most of this before, but it may be helpful for all of you. So let me go back to Blackboard. Okay, I'll try to make this as quickly as possible. Okay, content. And let me make sure I'm in the right course here. No, this is Math 112. Let me get into Physical Science 112. Okay. Now someone has a microphone on. I'm picking up some background stuff. It's not bad, but just want to let you know it is there. Okay, so you know that this is how you get to, this is the Physical Science 112 tab on Blackboard. So when you click on that, it opens up, and I'm going to scoot you. You can't see this, but I can. I can't get to everything with you sitting there. Okay, so I've moved you down some. We don't have any new people in. Should have 5 people here. 1, 2, 3, 4, 5. Got it. Okay, so I'll close that out. There was the Zoom announcement, so we got that. Okay, now you can start here if you want to. There's nothing special here. It just is, well, actually there is. It's been so long. The course syllabus is here, and there's only short time left in it. Your course syllabus agreement page, which I think you did the first week. Okay, there's the information on the textbook, which is in the syllabus too. Now anything here that when you click on it, it underlines and has an icon, you can do that. Okay.
It's about to be on the screen.
Oh, that's right. I'm sorry. When I went there, it took it off the screen. Sorry. Okay. Now can you see that?
Yes, sir.
Okay. So let me go back up. Okay, it says start here. Now that start here, notice it doesn't have an icon. It underlines, so you had to open that. I'm going to scoot you down a little bit by this arrow. It was down, okay, and the only way to open it is by flicking it so it goes up. And this, I think, is a fairly worthless thing, but it's in here. I left it there. Here's the course syllabus. You can go see that anytime. You've already done your, I think you did your course syllabus agreement page. Here's more information on the textbook. That's also under the course syllabus, so it's in there too. Americans with Disability information, that was also in the syllabus. So that's that stuff. Nothing we're currently using that much now except wrapping up the syllabus. Okay, so I'm going to close that out. I thought I was closing that out. I was actually opening this. This is more stuff from the navigating the course, blah, blah, blah. It's got a video in it and stuff. I haven't even looked at that. I didn't realize that was there. Sorry. Okay. So anyway, that was the start there. Here's my contact and office hours. Now let me see if I change that. Yeah, I changed it when we went to the second mini term. So that's that. My instructor contact information, you can click on that and see any of that you want. Okay. Then when you open something like this, you close it by the X over here. Okay. Now I'm going to close that out. Now, the weekly assignments and activities, that I think is what you were talking about. I'm going to explain the stuff here. Okay. Now, you're right, we did 2 labs a week, and sometimes we had a test. Well, no. The first week we only did 1 lab. And so in here you'll see the overview of what we were going to do, the instructional materials, and that's where the lab is located, the blank lab. This is where you can turn it in if you want to, but you don't have to. Here is the first test. You can turn it in there, but you don't have to. Now, why do I say you don't have to? Because here's the other option. Up here, you see this little envelope? That's Blackboard messages. Okay, hold on, let me get Valerie in here. Okay. Now we got someone at the bottom part of the alphabet holding it down. We're grounded now. So here we have the Blackboard messages. If you click on that, you will see where Mia sent me messages, Angelita, and stuff like this. In yours, you won't see all these unless y'all sent messages back and forth to each other. But somewhere down here, you will see, okay, here. Here's one place where I printed the lab. Oh, no, I'm sorry. That was an answer to somebody else. Sorry about that. Right here. All course members. Here's attached as a copy of Test 5. It was over there in the weekly stuff, but it's also here. Here's a worksheet for Lab 13, okay, that we should do today. Here is a worksheet for Lab 12, which we did on Tuesday, okay. I have it under the instructional materials, but I also put some of them here. I didn't always put all of them here. I just started this at the end. But the point of all this being, now it goes on to page 2 here. Now, when I answer some of these emails, there won't be as many. There's a Chapter 4 test. It was in the weekly stuff. It's here too. These are things I've answered to students before. Let's see if there's any other. This is mostly my responses to people here. Here's the Chapter 2 test. It was in the weekly stuff. It's here too. And just because it's in the weekly stuff and here, that means you can also turn it in through the weekly stuff, or you can turn it in under Blackboard messages right there, the envelope. All you have to do is when you click on that, I won't actually do one. Well, I'm in it now. I'm sorry. Click on the plus sign here. And when you click on the plus sign, now I've got to move you out of the way. Well, I'll move you down here. Okay. It says recipients, and if you click here, you can find my name. If you want to add a file like a lab, something like that, click here, and then you'll have a means to attach it. Okay, you can type me a message if you want to. So this is how you return anything. You can do your research paper this way. You can do any of the labs this way. You don't have to use those under the weekly things. You can do your tests this way. You don't have to use the ones under the weekly activities. You can do them all here if you want to. You can do some of them here if you want to, but this is another way. There's yet another way you can do it. Just go to email, okay, and attach to the file the lab, the test, the research paper, whatever you're wanting to send me. You can send it through email as well. You can't send it through Blackboard this way. Here's where you do Blackboard under messages, but you can send it through a regular email. I know you know how to do that because you've been emailing me some, okay. So that's how you send the other stuff. You don't have to have a place in the weekly activities. You can do it through messages, or you can do it through an email attachment. Does that make sense?
Yes, sir.
Okay. Now, let me go back to the content page, and I wanted to show you something else. Under week 1, I don't think it's still open. I'll move you out of the way again. Okay. No, week 1's not open. Okay. Under week 1. Okay. Now, I think you must have found this, instructional materials, PowerPoints, all that kind of stuff. Okay, at the top of every one of these weekly things, those are the PowerPoints that we either may have used or did use that week. Here are my recorded lectures, the YouTube videos. Everything we did in class, I don't think any of ours failed to load, but even if they did fail to load, then I kept out there the last time I taught the course when we covered that material there. So everything covered in the course is there under YouTube videos. The ones from the older classes are at the top, the ones from this class are at the bottom, and I think we just about cover everything in this class. I don't think we lost any days of YouTube videos. So you can click on that, go back and hear any lecture. You can watch us do the labs, because usually, in fact, I'll show this. Okay, I may have to move your name again. No, here we go. This was chapter 3 and 4, lab 5. That was from last time. 6.6 was from last time because we haven't covered all this. This was from last time, and that was from last time. Here's where this course started. See, we haven't finished chapter 8 and haven't done the lab here, so we'll do that today. Well, I didn't mean to do. Okay. Maya, you're the first new student we've had here. Gerald's been. Okay. Now, sorry, I didn't mean to get that started, but you see, you can listen to any of them and watch them. Okay, and like you see here, there will be labs. There's our lab 1, there's our lab 2, and in fact, just about every class from then on, there's a lab. Now, I forgot to put lab 4 here. It's there, you can tell. Lab 1, lab 2, lab 3, lab 4, I forgot to type in. Lab 5, every class. So if you, and there's lab, okay. Now, here's what happened on this day. You'll notice the time is short. It just shut down in the middle of the class. And then I had to pick it up again, actually not the middle of the class, at the end of class, 2.5 hours in, and then I just did the lab. So this is the class that day, that was the lab that day. And then there's lab 7, lab 8, lab 9, lab 10, and this one did the same thing. This one cut down before halfway through. It just shut down in the middle. I brought it back up and we finished. Okay, and there was lab 12. That's the one we did last Tuesday. So if you want to watch the labs and watch us doing the labs, you can do that, and that will help you. If you printed them out already, you can fill in the blanks as we're doing them. Okay, all right, so that's how you get the stuff to do the labs. Now I'm going to check out here. I don't need to sign in. I'm just going to close it. Okay, so that's the YouTube video. Now, there aren't any instructional videos, okay, but here's the handouts. There's the research paper instructions for the mini-term class. That's this class. So there are the instructions for what's expected in the research paper. Technically, it's due Tuesday. I'd love you to turn it in anytime sooner if you can. This is talking to everybody, not just Shay. Here is my locator card that shows when I'm in class, out of class, available, not available, when I'm at lunch, that kind of stuff. Here is the lab simulations that we use for most of the labs. Not all, but most of the labs we use that simulation. And there was the first lab there. You were absolutely right. There it is. And here was this was your library services for physical science. That's what that stood for. That the library sent me, so I put it here, and then I referred to it in all the others. Okay, so that's most of the course. I mean, every week has the same stuff in it, but in subsequent weeks, under recorded lectures, I'll say see the link in week 1. Under handouts, I'll say see the links in for research paper instruction and locator card in week 1. Here's where they are. Now I usually did put the lab link here. Occasionally I didn't get it done properly as a web link, so you might have to copy that onto your line, but most of the time if they're in blue and underlined, you can just click on it and go. And I think for the library link I said see week 1 for the library link. So that's most of that. Now, is there anything else? So you see in week 2, I'll close week 1, open week 2. Okay, the lab materials are here in instructional material. You can submit it here, okay, but you don't have to. Okay, wait, here's Angelita coming in. Let me get her here. Okay, top of the alphabet. Yes. Okay.
Why did I forget about class today?
I don't know. Floridian slip, I guess. Okay. I was just Shay's first time here, so I was sort of taking her through the blackboard. And by the way, I think I took everyone through the blackboard in the first day of class. So Shay, if there's anything I'm missing, go to the YouTube video first day of class for this term, and you'll see everything you need to know there. Okay, so that takes us up to, let me go on and close out this. That takes us up to week 7. That's where we are right now. Well, I thought it would open. There it goes. Sometimes Blackboard is really obstinate. Okay, there's the overview. Here's the instructional materials, including the 2 labs. I always put in the current week if there is any discussion, in case anyone wants to do it. So far no one's bit in any of my classes, so I would delete them at the end of the week because no one did anything. There's lab 12 and lab 13. I got them both in this week because there was no test or anything else to submit. And then week 8 will basically, I don't have it done yet, but we will, that basically is going to be a class on Tuesday. Probably not much of a class, but a little bit of a class on Tuesday. And if we don't get to the lab today, which I think we will, we'll get to it on Tuesday. If I don't give you your test today, I'll give it to you on Tuesday. Okay. Now, when it gets down here to exams, I haven't done this yet either, but that's where I'll put the final exam if it allows me to put it there. I always put everything, or pretty much everything, out on Blackboard Messages too, but the exam will go right here. So it won't be under week 8. It will be the last test will either be in week 7 or week 8. I don't know which. And the final exam will be down here under this one. Okay, any questions about any of you? This is not just Shay, anybody. Any questions about the setup here? That was Blackboard. So I'm going to get out of Blackboard, and I'll probably lose my, no I didn't, okay, but I'll go back to the PowerPoint. Okay, now trying to get the PowerPoint. Okay, there we go, and we'll go from current slide, and now that puts this stupid box in here. It fades in and fades out, but sometimes it blocks things that you need to see. I can't do a thing about it. It's a weird thing that I guess Zoom does, or the combination of Zoom and PowerPoint. I don't know why it does it. Okay, now I think we've got enough people here. I can go on and make all the announcements. So before we get going again, We barely got started on the class earlier, but before we get going again, let's go over how we're going to wind up the course. Not wipe it up, but wind it up. Okay? Now, we have class today. My guess is we're going to probably come pretty close to finishing just about everything we need in class today. I don't know that for sure, but the majority of it. Okay? We will stop at 5:45 if we go that long, and then we'll do that last lab, lab 13. It's out there under instructional materials. Now, this is one lab that will not be based on the simulations. This is one you'll be using the book, and I will be pointing out to you when we go where in the book you'll be doing it. Okay? And while we're doing it, I will pull the PowerPoints back up that show the things. Now, maybe not all of them are there, but I'll refer you to the page numbers and we'll do the lab together like we usually do. Okay? Now, so Tuesday technically is our last day of class. Now, if we don't finish all of Chapter 8 today, we'll wrap it up on Tuesday. I'm thinking we'll come pretty close to finishing it today, but I'm doing an awful lot of talking now, and we just took a fair amount of time to go through Blackboard, so we may not finish everything today, but we'll get most of it done. So on Tuesday, technically our last day of class. What does that mean? Now, wait, time out just a moment here. We found out last week, okay, that was Thanksgiving week, we had meetings Monday, Tuesday, and Wednesday. Okay, y'all were free, y'all were out, you didn't have to come to school. Everything we did was virtual, but we still were in meetings all day Monday and Tuesday and a good part of Wednesday. Okay, now one thing they told us that I had not known before, I'd been asking questions about, but never could get a good answer, and that was, where in the world are the student course evaluations? Okay, they finally came out with them either the week before Thanksgiving or during Thanksgiving week. Now, they sent an email to every student. The trouble is, I don't know how they sent it, because it wasn't the normal person sending it, it was the IT person. Normally it's the dean sending it. I don't know how she sends it, but it seems like most students usually get it. I've had one student, one very good student who's usually on top of everything, said, I didn't get the email. Well, we started investigating, and we think what happened is they must have sent the email through your new email address. I think that's the one with the A number in it. Have any of you seen actually the email may have called them surveys rather than student course evaluations? Have any of you seen them? Anybody? Yes or no? Is anyone still there? Did everyone leave already? Angelita's still here.
I didn't find anything.
Okay. Did you look?
I didn't even know we had a new email.
Ah, okay. That may be the issue then. Now, how in the world to tell you that? It should have come through the old email system, the information about the new email. Have you been checking pretty regularly your old email?
Yes, I got the email where they gave us like our A number and stuff.
Yes.
They told us that this was the new login, but they didn't say nothing about an email.
Okay. Has anyone learned anything about the new email?
Yes, what you have to do is go to the Lawson State page, and at the when you click on emails, it's going to take you to the very bottom and tell you the instructions on how to put in the new A number. Your password is going to be your
Birthday?
or something like
Yeah,
that. But it's
right.
going to give you that directions at the bottom, and then once you do that, it's going to take you to the new email.
Okay, so on the Lawson State web page, where on the web page is it? Is
Let
it?
me go to it right now.
Okay.
Pull it up.
I'm glad we're getting this said because I didn't realize they had been that slack on getting the information across. Because we didn't change our emails. Our
You're
email.
gonna go to.
Yeah.
I'm sorry.
No, go ahead. No, go
You're
ahead.
gonna go to email login, and once you click that up, it's gonna say student email, and it's gonna say give you the directions on how to use the new system.
Okay.
Okay. The username is gonna be your A number and Lawson State, and then your password is going to be exclamation LS and your birthday. So you got to go to this page and pull it up, but just simply go to email login, and when you go to the bottom of the page, it's going to give you all the instructions.
Okay. Now that's on the.
Actually, your password is going to be exclamation in all caps L Lawson State Community College LSCC and your date of birth, and it's a 2-digit month, a 2-digit day, and a 2-digit year.
2-digit year.
Yes.
When you do the student course evaluations, I think that's going to be a 4-digit year, and it may come first. But all those instructions are out there. What I'm going to try to do now is pull up the Lawson State page. Okay, well, I shouldn't have done it there. Let me close this. I'll be right back. Okay, let me go to. I probably lost you right there, but let me go to Lawson State web page. Okay, that's the home page, right? Okay, let me pull this up. Can't. Lawson State home page. Where is it? There it is. Okay, can y'all see the Lawson State home page? All right. Now, y'all walk me through it because I haven't been here before. I mean, I've been on the page, but I haven't done the thing. Is it scroll down? Tell me what.
Okay, I'm sorry. Yes, scroll all the way down. Okay, are you already at email login?
No, that's what I'm looking for.
Okay,
Scroll back
yes.
up to the top.
To the top. Okay. Okay.
Okay, right there in that blue bar where you see virtual advertising center, my Lawson campus, Blackboard, email
Right.
login. Hit email login.
Okay, this one right here.
No, go
Up.
that blue right there. Go over to your.
Oh, there you go. That one right there. Does everybody see where we are there? Email login. It's in the light blue, not the dark blue. You have a dark blue set of tabs at the top of the page, then the Lawson State logo, then a dark blue set of tabs below that, and then a light blue set of tabs here. And this has changed since the last time I was here because it used to be, my Lawson campus used to be over this way, I think. But anyway, over from that, there's your email login. Click on that. And then it says new and returning students, blah, 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 blah. Okay. Now, where do you go next? Right here, student email. Right there?
Yes, sir.
Okay, student email. Click on that. I'm not a student, so I don't know what it's going to do with me. Oh, that took me to my email. Okay, and there some of you are there. I can't do anything with that, so let me go back. Well,
And if you're already logged into Blackboard, it'll automatically pull up your emails when you click on it the way it did with yours just now.
okay, so if you're not, okay, well, let me see. I'm going to close this because I'm already in my emails. Okay, so you know where to go, and from that point on, you should be able to find it. Y'all are so good at navigating the web, I don't need to tell you how to do it. You could tell me how to do it because I get lost sometimes. But does everyone think they can follow it from that point on? I can bring it back if you need me to. Okay, anybody? Ooh, goodness, I just hit my funny bone that wasn't too funny. Okay, so Daniel, you think you got enough to get it? Okay, good deal. All right, then let me go back to current slide here. Okay, now did we finish everything about how to wind up the term? Okay, maybe not. We got as far as Tuesday. So Tuesday is technically when your research paper is due. Okay, y'all get an extra day or so because you're a mini-term course. The full-term courses, the last day of class is also theirs, but their last day of class was this week, okay? Your last day of class is Tuesday. So you get one more weekend to work on it if you haven't done it already. Now, as I tell everybody, and I've said over and over again, don't hold off things until the last day. Get them in. As soon as you get it done, submit it. I had some people who were thinking they had to turn in all their tests at the end of the term. Please, no, don't do that. Or all their labs at the end of the term. No, get them to me as soon as you get them through. Now, I'm behind in printing and grading, and I apologize for that. But Sharonica, Shay, you weren't here, but I had from the middle of October to the middle of November. I didn't realize it at the time. I knew I was anemic because I've got a mild form of leukemia, and sometimes that drives down the red cells as well as the white cells get out of control. But the treatment does even worse, okay? I mean, it knocks the white cells out completely, but does do harm to the red cells, the platelets, the hemoglobin, the hematocrits, and neutrophils, all that stuff. Nobody goes unscathed when it comes to that treatment. But the main thing it hits is the white cells, because those are the malignant cells. But I had a treatment mid-October, and right before the treatment, I had gotten so stinking tired, and they told me I was very anemic at the time, back when I did the blood work, and that's when they decided I needed the treatment, which I knew I did. But I was just so completely exhausted. I've never felt that way in my life. And then I had the treatment and I felt even worse. I knew I was anemic. And I thought, this is what anemia feels like, okay? So I drugged through the month. I mean, it was awful. And finally, when they were doing blood work to see about my next treatment, which I knew I didn't need, I did the blood work I talked them into letting me do it on a Wednesday so I wouldn't get there, then them prep me for an infusion and then find out I didn't need it. So I talked myself into letting me do it on Wednesday rather than waiting till Friday. And when I did it on Wednesday, I hadn't gotten home before there were 3 messages from the nurse saying not just that I was anemic, I was critically anemic. And they said, you've got to come in for a blood transfusion. I've never had that before in my life. So I had to go in, and on Friday, they gave me not just 1 unit of blood, 2 units of blood, 2, I guess, pints of blood, or whatever the bags are. And boy, I felt better almost immediately, okay? And have felt good ever since. I'm still anemic, but nothing like I was. But boy, for that month, I had the hardest time getting anything accomplished because I just ran out of energy so fast. And it's almost scary. I don't know what critical means, but it sounds pretty bad. I was that way for a whole month. So anyway, I'm behind in the printing. I'm getting caught up on that, and I'm really behind on grading because I don't have it all printed yet. So I'm behind, and I know some of you are too, so let's get it done together. Get me stuff as soon as you can. As soon as I get it, I'll print it, and as soon as I have a chance, I'll be grading it. Okay? So please do the student course evaluations. You may need to get your new email set up before you can even find out about them. So get that done. Get your research papers in by Tuesday before, if you can. Get all of the old labs in. As you finish them, send them to me, either by email or by Blackboard message, or if they have a place there in the weekly activities. If they don't, do it by either email or Blackboard message. Get me those in. Get me your test in. Try to get everything cleared out this weekend so next week you can only focus maybe on the Chapter 8 test, but definitely on Chapter 8 test and possibly, but definitely the final. Okay? I heard a big noise. I don't know what the noise was. Is anyone else waiting? I don't think so. Still only have 7 students here. That's amazing. 1, 2, 3, 4, 5, 6, 7. Yeah, that's all we got. So I may have to repeat that as more people come in, but anyway, I've got it done for most of you. Any questions? Oh, and then the final exam is due by Thursday. I'll give it to you on Tuesday. Now, I've asked this question before. I think there was somebody. Are any of you graduating this term, this spring? And I mean this fall, this term right now? Yay or nay? Okay, that's Amia. Okay, you have to sort of rush it a little bit. But I think if I give you the final on Tuesday, which is what I'm planning to do, you can have it into me because it's really easy. It's matching. That's all it is. So get it to me as soon as you can so I can get your grades in. I don't think it really matters because it's a virtual graduation, and if it winds up that not everybody has passed, it's okay. It doesn't really matter because you're not getting a diploma or anything. Even when you go through the real life graduation, you're not getting a diploma. You're just going through a ceremony. They mail you the diploma later. You come by and pick it up because they don't ever prepare them until they're absolutely certain everybody's got it done. So don't sweat, but I'll try to get all the graduating students in as early as I can. So Amia, you just get me your thing a little faster than the other folks. The other folks have until Thursday. If you can get it to me by Wednesday, that'll be great. Okay?
Okay.
All right. Anyone else who's graduating, same deal. Oh, and by the way, student course evaluations, when I was mentioning those, I know some of you folks were in first mini-term courses because some of you were in my first mini-term course. So please, folks, do the first mini-term as well as second mini-term because they did not have this ready to go in first mini-term. In fact, they've been fighting with Banner to get Banner to cooperate with SmartEval. That's the package we use, and they just got that resolved. Like I said, either the week before Thanksgiving or the week of Thanksgiving. So everything's running sort of late. Okay. Any questions before we hit the physical science now? This is where we left off last time. I'm going to go back a slide or two just so you can see. Well, I'm going to try to go back a slide or two. Okay. We talked about Bohr's theory. Before that, atomic spectra, that kind of stuff. We did somewhere here the Balmer. Oh, there it is at the bottom. The Balmer series of hydrogen lines. That's what we were dealing with last time. That's where we ended, but we didn't quite get to this slide. And this summarizes what you found out about the other. Now, something popped up there. I couldn't see what it was. It doesn't look like another student coming in. So, are there some chats? Yeah, there's at least one chat. Now, if you're sending a chat to me, go on and speak up, okay? Because if I open the chat, everybody's going to get to see it anyway, okay? So go on and get it done. All right. If you're sending it among each other, perfectly fine. Do it. Knock yourself out. Okay, so here's the quantum theory of the atom. This is what I started talking about before most of you got here. I think there were only like 3 people here when we started this. In classical physics, classical mechanics, okay, you always assume there was a 0 reference level when energy level was 0. In quantum mechanics, that's not the case. The lowest energy state is never, ever 0. It's called the ground state. You can't have 0 energy for anything, okay? So therefore, you have your lowest energy state, and that's the ground state. Now, according to their diagram here, that would make it appear this is the lowest energy state, and yet they showed this as the lowest energy state. I think this is the real one. But most things operate even above the lowest energy state. To get down here, I think you have to get awfully close to absolute zero, you know, and not many things get that low, okay? So here is where things are going down to. Now this is the hydrogen atom. This works for the hydrogen atom. Now the higher energy levels here are called excited states, okay? Here, 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 and there. Now, your electrons for the hydrogen atoms basically operate out of level 2. I guess maybe the proton by itself would be down here. I don't know, okay? But anyway, here it seems to be what you would call the ground state for hydrogen, okay? Now, if something excites an electron, now this was part of Bohr's theory, it goes up by a fixed amount. It would not go up to here or up to there or up to here. It goes up to here or there or there or there. They're fixed energy levels. Now these fixed energy levels are incredibly close together. This makes it look like they're way far apart. They're not. They're really, really close. Okay? But those are the fixed energy levels. And then when they fall down from these states, that's what gives you those spectra. This is that red spectra that we saw for hydrogen. This is the blue-green spectra. That's the lower level violet. This is the upper level violet. Okay? As they go down to the ground state for hydrogen. The photon energy equals the difference in the state energies. And the states are called 1, 2, 3, 4, 5, and 6. Okay? Now, later we'll be talking about something else that's called N. Don't get that confused with this. They may be slightly related, but not much. Okay? This is just a marker to say what state you're in. And the ground state is either down here or up here. It appears in this thing to be right there. Okay. Now, your photon energy, remember Bohr's constant? No, Planck's constant, H. H times the frequency is equal to the difference between those energy states. The high minus the low. This high minus that low. This high minus that low. This high minus that low. These are the energy states. Okay. Now, that's what this means. The photon energy equals the difference in the energy, the state energies. The hydrogen atom, as an example, these are your energy levels and these are your aligned spectra. They go hand in hand. Okay? So that explains why we see those 4 distinct line spectra for hydrogen. Now, I can't get it to advance. Okay. Now, Bohr worked this out. It worked out really nicely. It fit Balmer's series. Everything was looking good until he tried to do it for helium, the next atom. It fell apart. Okay, helium was way too complicated for his simple model to work. So shucks, all that, and all he got was one element covered. But that gave us a lot of information. Further experiments established a wave-particle duality of both light and matter. And there was a guy named Young, I can't think of his first name. This is over on page, oh, there was one other thing I meant to to point out. So let me go back and mention this. Notice here they talk about energy in joules. That's the one we're used to. And look how incredibly tiny those energies are in joules. However, because we're talking about electrons moving up and down in orbitals here, so an electron is a charge, a volt, and what is a volt is energy per unit charge, so this also gives you an energy, an electron volt. That is a incredibly tiny amount of energy, and that's what we have here. Now, I have never really heard or figured out why they go with negative numbers. Remember, this number is less than that number. This number is less than that number because a larger negative number is more negative, okay? So this is would be your ground state, or this is your ground state, and then the difference between these are your other. The difference between them is positive, okay? Not negative. Energy is positive, but they put the energy levels at negative numbers. So it's a little hard to wrap your head around, but that's what it is. So electron volt is a measure of incredibly small quantities of energy, as in those little photons of energy. You can't measure them any other way. I mean, if you measure them this way, look how many decimal places you've got to the left. Way small numbers. So these are much more usable numbers. Okay, I wanted to say that before we moved on. Okay, just making sure we got everything covered. Now there is an example. Oh, and let me go back one more time. Okay, this formula right here, E sub n is equal to E sub 1 divided by n squared. Okay, and the E sub 1 is this one down here. There's your 1, so that's divided by negative goodness gracious, why does this do that? Negative 13.6. Okay, and in your book it's just given as E sub n is equal to E sub 1 over n squared. But the E sub 1 there that they put in your book is this one down here. Not this one up here, but this one. So that has to be the ground state. Okay, why they show these only going to level 2, maybe that's the only as far as they go in hydrogen. I don't know the exact answer to that. So let's now do example 8.4. An electron in a hydrogen atom jumps from the excited energy level n equal 4 down to n equal 2. It jumps from here to there. Okay, what is the frequency of the emitted photon? Okay, well, we can do it right here, and I'll get my pen and see if I can do it. I don't have a lot of room to write, but I think we can. Here's your formula right down here, if I can get the pen to show up. Come on, pen. There it is. Okay, HF, we're looking for the frequency, the F part, so we're going to be dividing by H, is equal to EH minus EL divided by H. I'm going to divide both sides by H, and that will give it to us. Okay, the EH is given right here. Now, do they give this in electron volts, or no? They must be doing in joules, because H is given in joules. So here is what we do. We subtract the low from the high. Here is the low, there's the high. It's going from 4 to 2, so do that subtraction. And if I had room on the slide, I would write it out there, but I really don't. So I'm about to lose my pen, and it's a very expensive pen. I don't want to drop it on the floor. Okay, I'm going to do it on my calculator. Okay. Pull up the calculator mode. It's my phone. Okay. I'm going to turn it sideways so we can use scientific notation. And the high level is 1.36. Now, I have to do it this way. Your real calculator probably will allow you. I have to change the sign of that. Then I do the EE for your exponent, and that was negative 19. So I type in my 19 and do the negate that again. Okay, so there I have that. I'm going to subtract from that, and there you see it written out. I don't know where my camera is now. I can't see my picture, so I can't show it to you like I normally do. Why Zoom decided to change things today, I don't know. Or this afternoon. This morning, all three classes worked fine. Okay, and I'm going to subtract from that what the n equal 2, and that's 5.44. Negate that. EE 19. Negate that, and do an equal sign. The difference between those two is a positive number, because this is a smaller positive number. That's smaller negative number, meaning it's a higher number. This is a more negative number, meaning it's more negative, so it's lower. So the difference between these two is 4.08 times 10 to the minus 19, if you can see that. Okay, we're going to take that and divide it by Planck's constant. Now that one I don't have memorized. I always look it up because I don't trust my memory, even if I could memorize it, which I don't ever waste time to do. So let me see if I can find Planck's constant. It was back here a couple pages back. Where is it? There it is. 6.63 times 10 to the minus 34 joules per second. So this is 4.08 times 10 to the minus 19 joules, dividing that by 6.63, so divide it by 6.63, EE 34. That's an incredibly small exponent. Negate it, okay, and then press equal. Okay, and oh my word, look at that frequency. Okay, and this will be in per seconds. So let's go back and see if we're anywhere close. It's an incredibly large number. 6.15 is what I got. Let me see if that's what they got in the book. 6.15 times 10 to the, and why they didn't left scientific notation, I don't know. 3, 6, 9, 12, and 2 more would be 14 times 10 to the 14th per second. I'm sorry, per second. 1 over second. What did they get in the book? 6.15 times 10 to the 14th hertz. And that's what a hertz is a per second. Okay? So you could list that as, if I could get the pen to show up somewhere down here, as a hertz. HZ. Pretty high level frequency. But if you think back on it, that was in your blue-green spectrum. Okay? And that sure enough is what you got. 6.2 times 10 to the 14th hertz. That one right there. This one right here, going from level 4 to level 2. There it is. So we didn't actually have to do the thing, but this just shows you it works. All right. Any questions on that? Okay. That's approximately the blue-green line in the hydrogen spectrum. All right. That's the quantum theory of the atom. Now we get into 8.3, which is, even though we've been talking about it for a while, we get into quantum mechanics. Okay? The Bohr model, Bohr theory, unfortunately, only modeled the line spectrum of hydrogen. Did a great job of that, but it didn't work for anything further. So they had to do further experiments establishing, and they wound up into something they really weren't expecting, I don't think, the wave-particle duality of light and matter. Now, actually, they may have been expecting it, because remember, I think it was Max Planck said that the energy doesn't come along in a continuum, but in little energy packets called a photon. And those photons acted like a little chunk of something. It didn't have any mass, so it couldn't be matter, but it acted as if it was matter. And I wish I could find the name of the guy. I've heard it before and I can't remember his name. Young, I can't remember his first name, but he came up with a two-slit experiment, and he produced interference patterns for both photons, which is totally light, and electrons, which is totally matter. Okay, and he showed that with two slits and firing a beam of photons through the two slits and a beam of electrons through the two slits, you got interference patterns that looked fairly similar. Now, what was different about them was the distance between the slits had to be significantly different. Okay, but they did produce similar patterns. Okay, so that gave rise to the fact quantum mechanics does exist. Who understands it? Not many people. Okay, in fact, even the experts, I think, still get confused with it. Okay, now, one guy, Louis de Broglie, I believe he was French physicist, though that doesn't sound like the Louis sounds like a French name. De Broglie, I'm not sure, but around 1923, he postulated that matter does indeed travel in waves. And remember, we were calling it the wave-particle duality. So matter, which has particles, does travel in waves. Light, which is all waves, acts as if it's traveling as a particle. Okay? It's not really a particle, but that's what it is. So the matter waves were postulated by Louis de Broglie. When I took the course, it was quantum mechanics in college. I had an Irish professor with one of the strongest brogues I've ever heard in my life. And when he said de Broglie, I mean that R rolled like crazy. Okay, but anyway, the wavelength was related. The wavelength of these waves was related to the momentum, which is mass times velocity of the waves. So there's the connection between the duality between waves and matter. Matter waves in atoms are standing waves. Now, what do we mean by that? Now, if you remember back, one of Bohr's rules was, where was it? The next one back, wasn't it? Nope. Yeah, here we go. The radiation, okay, electrons only exist in certain allowed orbits. Within an orbit, the electron does not radiate. And part of the reason for that was that the electrons, and Bohr didn't know it at the time. Later, de Broglie came up with this theory, and this is what allows it. Okay? Now, it seems like they got the cart before the horse here. Okay. Here is the formula that de Broglie came up with. The lambda, the particle wavelength. Okay? Particles, matter, have waves. The particle wavelength is good old Planck's constant, showed up again here, divided by the momentum. m times v. Now, this stuff at the bottom of the page is blocking it. Didn't want that to happen. And you can't see this. Yuck! Everything's blocking it now. This thing will fade out in a minute, but still, I don't know if you can see it. I can't see it. M is the mass, V is velocity. This is particle stuff here, not energy stuff, particle stuff. And yet this is dealing with wavelength, and that's what you get. Okay? Now, this is what we mean by standing waves. In an orbit that we usually represent as a sphere, or in two-dimensional as a circle, in reality it's not that. It's traveling in a wave pattern. This is an electron we're talking about here, and this is what we mean by a standing wave. The orbit, so to speak, is fixed, is continuous. It doesn't move outside that. This would not be a standing wave because it starts here and winds up there. It doesn't connect. A standing wave does connect, and this is why there's no acceleration, no loss of energy, even though it is moving in a circle, because it's a standing wave. So that's why Bohr's number 2, that as long as you're within an orbit, you do not have any loss of energy. Okay, this only works in quantum mechanics because you have to have that wave nature of the electron, and you don't have that in classical mechanics. And this is what happens in a wave, at least according to de Broglie. Okay. Now, once that was developed, then along came Erwin Schrödinger. Now, he has come up with one of the most complicated equations I've ever seen in my life. The book doesn't even give it. Thank you very much. And that's on page 316 or 216. Before we go there, we do run into the next couple of examples. So let me move back a slide and let's see if we can do the 2 examples. What is the wavelength associated? Let's go back one more. The wavelength associated with a 0.150 kilogram baseball. Boy, in my Cal 3 class, I have a baseball player, at least one, and he would appreciate this one, maybe not. So what is a wavelength? That's what we've got down here. So let me see if I can get my pen to write. I'm going to repeat what's down here, but do it up here. Lambda is equal to, oh, here comes Tobias. Hope he wasn't waiting long. I didn't notice him. He was on a blue background, so I didn't even notice it. Tobias is here. Okay. Now, Tobias, I know you just got here, but earlier we talked about how to wrap up the term, and basically we have class today. We may or may not. I'm beginning to think now we won't finish chapter 8 today. I was thinking we might, but time is slipping away from me here. So we will finish chapter 8 on Tuesday, but hopefully we'll get far enough to do the lab today. Okay. Your research paper is due by Tuesday. Now back up a moment here. Recently, as in Thanksgiving week, which is last week or the week before that, they finally got the silly banner program that we're having to use now to accept our student course evaluations and got them to work together. So your student course evaluations, which the way it's expressed in the email that was sent out, your surveys, okay, that means student course evaluations, are now out there. But all indication is they're only out there on your new A number email accounts. The old email account, which was your first initial last name, then the 4 digits of your old ID number, .students@lawsonstate.edu or something like that, whatever that was, that email is going to go away sometime. It's still functioning now, but they did not, as far as I can tell, put the evaluations, the surveys on the old email. They only, as far as I can tell, only put it on the new survey, on the new email. And many of the people in the class did not know how to get access to new email. So there is a place on the Lawson State web page, the main page, homepage of the Lawson State web page. There's a series of blue tabs at the top of the page. Then there's the Lawson State logo, and then there's another set of dark blue tabs right below that. Then right below that, there's a series of one line of light blue tabs. About middle of the page there is one that says, what does it say? Email something. I can't remember exactly what it is. Find the one that says email and click on that, and I think you'll be able to find how to access your new email. You are given a new A number, and that new A number is part of your email. Okay, and then what your password is given there, and that has something to do with what was the first part of it? I think Valerie was telling us, or maybe it was Angelita. There's something, and then the last part is your birth date, but it's only a 6-digit birth date, year, month, day, year, or something like that. But there was the first part of it. So anyway, it's all out there. But then when you go to do the survey, I think your password is an 8-digit birthday, and I believe it starts with a 4-digit year, then a 2-digit month and 2-digit day. So you have to pay attention. One password is one way and another password is another way. But anyway, once you got it, it's pretty easy to maintain. Your research papers are due on Tuesday. Get them to me earlier if you can. Okay, Valerie, did you have something to say? You just popped up.
No, I'm sorry. I was about to comment on the password, but you were correct.
Okay, is that right? What was the first part of it? It wasn't
Exclamation.
That's it. Okay. LSCC. That's it.
In all caps. Yes.
In all caps. Okay. So your password is exclamation point, capital L, capital S, capital C, Lawson State Community College, and then your birth date. 6 digits, right?
Correct.
Okay. I couldn't remember what the first part was. Thanks for providing that. So anyway, there's that. Okay, let's get back. Oh, here comes Jacob, and we got to go through it all again, don't we? Okay, I'm glad more people are coming in. Okay. The group in the middle of the alphabet is really taking over here. We got 5 in a row there. Skip one and get one, skip one and get the last one. Up at the top part, at least one person withdrew, it looks like. And then you have one at the very top and skip one and another one. So we're getting a reasonable crowd in, but not as big as I wish we had. So Jacob, we'll finally get this done maybe at some point. First, they finally have opened the student course evaluations. Please do them. Some of you were in first mini-term classes. I know that for a fact because you were in my first mini-term class. But others of you may have had other first mini-term classes. Please do the student course evaluations for the first mini-term as well as the full term and second mini-term classes. Okay? Now, you'll probably be asked to do certain other surveys, like for registration or library or food service or something. do as many as they ask you, but especially do the student course evaluations. Okay. Now, it seems like they only publish those under the new emails. Now, if you didn't know you have a new email, you do. It's called the A number email. All of you were issued new A numbers. Those are your ID numbers. Your old 7-digit ID numbers that we used for the old system, that doesn't work anymore. Your new A number is a bunch of digits. I don't know how many. A followed by a whole bunch of numbers. I think the first two are usually zeros, but anyway, that's your new email. Okay, now that's part of your new email address, but to get all the information about it, you go to the Lawson State web page, the main page, the home page, and then there's a set of dark blue tabs at the top of the page. Then there's the Lawson State logo with not much else in the next group, and then you have another dark blue set of tabs right below the logo, and then right below that second dark blue tabs is a set of light blue tabs. And right about the middle of the page, there's one that says something about email. I don't remember how it's phrased, something about email. Go to that, click on that, and it tells you what your new email is, what your password is, all that kind of stuff. And the password is exclamation point, capital S, capital L, capital S, capital C, Lawson State Community College, followed by your birth date, 6 digits. And I believe it's month, day, year. Is that right? All the information's in there. When you get to your new email, then you'll find in your new email the instructions for how to do your student course evaluations, which they just call surveys. Once you get on the surveys, your login for that, I'm pretty sure, is an 8-digit. Your login is whatever it is, I don't remember that, but and all the instructions are in there, but your password, I'm pretty sure, is an 8-digit password, and it's 4-digit year, 2-digit month, 2-digit day. So it's not in the same order, and 4 digits on the year, not just 2 digits on the year. Okay, so it's a lot of differences there and slight differences, but that's what you do to find out to do your student course evaluation. Please do them. Take the extra time, get it done well. Okay, then in addition to that, do your student course evaluations. Your research papers are due Tuesday. If you can, get them to me beforehand. You may have already gotten them to me, I don't remember. Okay, but get them to me beforehand if possible. Get me all your old labs and tests in before Tuesday if possible. Get as many done as you can, as rapidly as you can. Don't hold off. Send them to me when you get them completed. Okay, remembering they're all out there on YouTube videos, every one of them. I may have forgotten to list it there, but they're all there in the classes where we did them. Okay, and the blank sheets and stuff are in the each weekly activity under instructional materials. That's where the blanks are, and that's also where the link is for the simulation, if that was using a simulation. Most of them did. Okay, get me all your old labs, all your old tests, if possible before Monday, and get them to me when you can. I'll be printing them as fast as I can. Y'all can get way ahead of me because there's a lot more of you than there are of me. And this is what's really such a pain about teaching virtually. It used to be you handed stuff in and I graded it. Now I have to find it, print it, and then grade it, and that takes a whole lot longer. It doesn't seem like it would, but it truly does. Okay, and then on Tuesday we'll wrap up class. That's the last day of class. We'll probably finish chapter 8 that day, and then I'll give you your final exam that after class that day. It'll be a short class. There will be no lab on Tuesday, just class, and it won't take long to finish class. Okay, we were getting ready to do example 8.5 on page 215, or if you got the little book, it's 8-11. Okay, and that's why I just written down lambda equal. Okay, what is the wavelength? That's what lambda is, associated with a, okay, I'm going to write the formula because it may be blocked out. Here it is, the formula. Lambda is equal to h, which is Planck's constant, over mv, which is momentum. Now this is the wavelength for a particle wavelength, okay? Actual piece of matter. A wavelength for energy, okay, like electromagnetic waves and things like this, they don't have mass. That'd be a zero mass. So this won't work for them. It only works for particles. Now this is not a very small particle. So you're not going to get a very significant wavelength here. It's a baseball, okay? And it's a 0.150 baseball, okay? So let's write down, if I could get my pen to show back up. It keeps disappearing. And where it goes, I have no idea. There it is, okay. Planck's constant is 6.63 times 10 to the minus 34th. Talk about an incredibly small number. And this is a joule second. And that's divided by the mass of 0.15 kilogram, 0.15, and they actually put in the book 150 kilograms, with a velocity of 50 meters per second. Okay, now that means this joule up here we need to put in its fundamental units. Well, joule is a Newton meter, but what's a Newton? A Newton is a kilogram meter times another meter will be a meter squared per second squared. So that's what a joule is, a kilogram meter squared per second squared. Here, this kilogram will wipe out that one. This meter will wipe out one of the meters up here, and this second wipes out one of the seconds here, and this second wipes out the other second there, and that leaves us with a meter. That's the only unit you have left, and I don't know what's making that noise. Let's see if I can find if anyone else is trying to get in. We should have 9 people here. I don't see any new chats or anything, so I don't know what that noise was. Okay, so we've got our unit in meters. That's a wavelength. Okay, so let's get our calculators, phones, whatever you're using. Okay, because it's got significant scientific notation. I'm going to turn it sideways, get it in scientific mode here. I don't think I need the second on here anymore. Okay, so what we have is 6.63 EE, don't ever do times 10, do EE 34. Now I have to do the 34 first and then change the sign. If you've got a real nice scientific calculator, you can do the little negative sign that's in parentheses, and that you type that first and then do the 34. So that's your Planck's constant. Divide that by, first we're going to divide by 0.15, because you don't need that extra 0, 0.15, and then divide again by 50. And you get an incredibly small number. The wavelength for that baseball is, if I could get the pen to show back up, 8.84 times 10 to the minus 35. And that would be meters. That's the one unit you got left. That's a unit per length. That's it. How many decimal places do you have in front of that thing that you move that? That would be 0.0000000. That's 6, 000, that's 9, 000, that's 12, 000, that's 15, 000, that's 18, 000, that's 21, 000, that's 24, 000, that's 27, 000, that's 30, 000, that's 33, and then 2 more zeros. An incredibly small number. 8.84 times 10 to the minus 35 meters. Incredibly small. Okay? Now, let's look at something that's a bit smaller, like an electron. What is the wavelength? This is a baseball, the wavelength of a baseball, which I can't get my pen to write. Where in the world is my pen? There it is. This is the baseball. Let's now do the wavelength of an electron. The wavelength of an electron, that's my symbol for an electron, with a velocity of 6.1000 times 10 to the 6th meters. Okay, so this is going to be, same formula, 6.63 times 10 to the minus 34, and it's be the same units, so I'm just going to leave a meter up here. We already dealt with our units before. Ooh, that went badly. Divided by the mass of an electron. Now this you have to go to either the front inside cover of the book, the back inside cover, somewhere you have your physical constants there, and the electron rest mass is 9.11. That's the mass of an electron. If I could get my pen to show back up. Where, oh, where are you, pen? I can't find it anywhere. Oh, there it is. Okay. 9.11 times 10 to the, and you thought Planck's constant was small. This is pretty small, minus 31. So not quite as small as Planck's constant. Okay. And that would be kilograms. And that kilogram is going to cancel the 1 from your joule, just like we did up there. So I'm going to leave that off for now. Times, and the velocity of this was 6.00 times 6 times 10 to the 6 meters per second. And they will cancel out the things just like they did up here too. Leaving you 1 meter. Okay, so that's why you wind up with a meter up here. Okay, now let's pull out our handy dandy calculators and see what this gives us. I'll clear that. 6.63 EE negative 34. Do the 34 first, I have to, and then negate it, divided by, that gives you exactly right, 9.11 EE 31, negate it, divide that then by 6 million, that's 6 EE 6, not a negative there, 6, and hit the equal sign. And this time we got another small number, but not nearly as small. It's 1, where did my pen go now? Can anyone see the pen? There it is. Okay. 1.21 times 10, and I've got a bunch of zeros here, so I have to stop and count them. That decimal moves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the 10th. Where are you, pen? There you are. 10 to the 10th meters. 10 to the minus 10 meters, sorry. Moved it to the right. So that's a considerably larger number than that one. The baseball is so incredibly tiny, you'll never in your million years measure that wavelength. This one down here, though, that's only a tenth of a billionth of a meter, which is a pretty small number, but it's much bigger than the 6.63. So let's see how the book did. 1.21 times 10 to the minus 10th meter. Good for them. Okay. So that was de Broglie's matter waves. And that led to wave mechanics, which is what Edwin Schrödinger came up with. And like I said, he came up with a wave formula that would blow your mind. I mean, it blows my mind, and I've had all the math that I need for it, and it's just out of this world. Wave mechanics were developed by Edwin Schrödinger. This sort of replaces what Bohr was trying to do that only worked with a hydrogen atom. This treats atoms as three-dimensional systems of waves. Okay, now that in itself is really interesting. How do you have a wave with crests and troughs in it in 3 dimensions? It is a crazy looking thing mathematically. It contains successful ideas of the Bohr model and much, much more. So it describes the hydrogen atom really well and other mini electron atoms. But of course, the more electrons you have, the more complicated your waves and everything else gets. Okay? But that forms our fundamental understanding of chemistry. All this is to get to say that statement there is that forms our fundamental understanding of chemistry. Now, we knew chemistry long before we knew Schrödinger's wave mechanics, but this tells you why. Okay? So, here's the quantum mechanics model. This is on page 216 or 8-12 if you got the little book. The quantum numbers specify different electronic quantum states. Now sometimes these are, and they're mostly dealing with energies, but they just call them quantum states. Now you visualize these things. You can't ever see them. These are incredibly tiny. You visualize these using wave functions, which to me is not very visual, and probability distributions, again, which is not very visual. Okay? It's made up. The electrons are delocalized. You can't say, there it is, or there it is. No. If you ever were able to determine where it was, you can't measure anything about it. Okay? So there's a whole nother thing we'll get to maybe a little bit later. Now here's what we mean by probability distribution. The electron, this is one electron, has this probability of being in any one of those dots, okay, at any time. Now, sure enough, most of the dots center right around there, with a significant number right around there. But you still have quite a few outside of that. This would be approximately your 90% probability volume, pretty much inside this imaginary circle there, okay? That would be 90% of the possible locations for that electrons. They're delocalized, they're somewhere in there. You got a 90% chance of it being there. 10% chance it's somewhere outside there. Usually we don't deal with that, okay? Now, your quantum numbers, though, really don't take that much into account. They probably do on some level, but we can deal with them without really getting too bogged down with that. Okay? Now here are your electronic quantum numbers in atoms. There are 4 of them. The first one is called the principal quantum number. Now I said this earlier, they use the letter N. Now, it probably is dealing with the same N that we used in the Bohr model, in the Balmer series. You know, it's that same N. Only now it means energy level. And that's what it meant there too. And what does that stand for? The average distance from the nucleus. So the smaller N is going to be closer to the nucleus. The larger N's are ultimately further and further away. So they're not really energies. They are distances from the nucleus, but that relates to their energy. Okay, so there's the first one, the N quantum number. The second one is the angular momentum quantum number, and that's L. Okay, that's not a 1 or an I, that's an L. That has to do with not how far from the nucleus, but what kind of spatial distribution you have. The one they showed back here, that's an quantum number 1. It's a spherical distribution. Okay, I just know that from before. Now these are labeled not with numbers like 1, 2, 3, 4 like N is, but with letters. Okay, and actually I said that wrong. That one that I showed you before on the previous page, that's an S quantum number, angular momentum quantum number, L equal S. Okay, that sounds sort of nuts that you're using one letter equal to another, but the angular momentum quantum number for that spherical shell is S. Then you have P shells, D shells, and these are actually subshells. These are shells, okay, average distance from the nucleus. These are subshells. The spherical one is S, the next one is P, the next one's D, the next one's F. Theoretically, they keep on going from here, G, H, I, J. In reality, we don't ever use those unless you have some super excited situation. We're not doing that. We're only going to use these first four, S, P, D, and F. Now, I'll show you a picture of what they, well, let's see, maybe we got it now. Okay, here is an S orbital for angular quantum momentum number S. This is a P orbital. The S orbital, there's only one of them per N. Okay, only one S orbital per N. The P orbital goes along each of your coordinate axes, so you have one on this one on this one, and one on that one. So you have 3 possible P levels for every N. Okay? Now, those are your 3. One on this one. Where is it? There it is. One on that one, and one on that one. Those are your 3 P orbitals for every N that you have. Okay? Then, okay, let's see if will they show the others. No, they don't. Okay? In your book, they do. Okay? But it's a very hard thing to see and even harder to visualize. Now, oh, I don't even know where my camera is, so I don't know. If you've got a book, look on page 217 or 8-13 and you'll see the representation for the D. The P is hard enough to tell. You see one's going on the x-axis, one's on the y, one's on the z. But then the D orbitals, they're all over the place. You have 5 sets of lobes. That's a total of 10 lobes. 5 sets of lobes. Okay, and we'll go on from there. So here's basically what you do. The S is 1, the P is 3, the D is 5, and the F is 7. So you're going up by your odd numbers here. We don't mess with G and H, don't even worry with them. Okay? Now the next is what they call the magnetic quantum number. And they don't list it as a letter, and they don't list anything about it. Okay? But we'll talk about what that means a little bit later. And then finally, we have the spin quantum number. Okay? The spin quantum numbers is really simple. There's only two. One's up and one's down. Quite often they'll say plus 1/2 and minus 1/2. Plus being up, minus being down. And since electrons can go anywhere they want to, how do they know what's up and down? That's just what we use, okay? And I can't read the word under there. Spin, electron spin orientation. We just say it's either up or down, okay? And that's the spin quantum number, okay? Their spin up and their spin down, okay? So use right-hand rule up, right-hand rule down, okay? That's how we distinguish. Now again, we didn't have anything to tie us into magnetic quantum number. We'll get there a little bit, just graze it just a little bit. All right, now here's what we've got. Here are the quantum numbers and the electron distribution for n equal 4. Now, what that means is 4 main energy levels, okay? Only going up to 4. At energy level 1, that's your n equal 1. That's your first quantum number, okay? You only have an s suborbital. This is an orbital 1, s suborbital. It's the spherical one, and it contains 2 electrons. One spin up, one spin down, okay? Maximum number of electrons, 2. Now, when n is equal to 2, you can have 2 sub-levels, one s and one p. Okay, the s can only hold 2. The p's, there are 3 p's, and each one can hold 2. One spin up and one spin down. So you can have a total of 6 electrons in your p suborbital. So that means in energy level 2, you have 8 electrons. Okay, when n is equal to 3, you have only one s, but it can have 2 electrons, one spin up, one spin down. 3 p's, each one holding 2 electrons, one spin up and one spin down. That's a total of 6. D can have 5, but they have 2 electrons each, so that's a total of 10. So you have 10 and 6 and 2, a total of 18 electrons when n is equal to 3. And we'll see how this plays out later. When n is equal to 4, you can have one s, okay, that can hold 2 electrons. 3 p's, that can hold 6 electrons. 5 d's, that can hold 10 electrons, and 7 f's, it can hold up to 14 electrons. Now, not always do they have all of them filled, but that's what the maximum. That gets us up to 32. Well, on the periodic table, we can't really relate it to that yet. We will, okay? But that's the maximum you can do up to n equal 4. When you get to n equal 5, you'll see you never go to G, ever, okay? And we'll see that why that's the case later, okay? So this is the table. Oh, and by the way, I meant to tell you, top of page 217, which is 8-13, there's a Science and Society Atomic Research. It's a good encapsulation of what we've done so far. First, J.J. Thomson investigates the cathode ray tubes and discovers electrons, negative charge mass. Okay, but can't come up with any more than the charge to mass ratio. Then Robert Millikan, with his oil drop experiments, was able then to determine the charge on an electron, which then, when he went back to Thomson's work, could determine the mass. Okay, then Ernest Rutherford came up with the gold foil experiment, and that one found out that it wasn't a bread pudding model, it was actually a nuclear model. All the mass is concentrated in a tiny little nucleus, and most of the volume is occupied by very, very incredibly small electrons, so most of everything is nothing. open space. Then Niels Bohr proposed a solar system model of an atom by applying the quantum concept. That's basically kind of what Rutherford had suggested. And then finally Erwin Schrödinger proposed a model of atoms based on wave nature of the electrons, and that's what we're getting at with these quantum numbers. Okay, a real short and sweet way of talking about it. Now, somewhere in the middle of this is this thing called the Heisenberg uncertainty principle. I don't think that shows up on the slide here, but it is in your text. And basically what this says, you cannot measure the exact position of a wave because a wave is spread out. One cannot specify the position and momentum of a spread out electron. If you ever thought you knew where the electron was, there's no way you can calculate its momentum. If you figured you could figure out what the momentum of an electron was, there's no way you would have any idea where it was. So you cannot get position exactly or momentum exactly. It's all a guess, okay? But that's Heisenberg's uncertainty principle. Now, I overstated that, but you can read that. Okay. Now, the table we have right here is on the top of page 218. Okay. Now, we've set it up for how our electrons are configured. Okay. The arrangement of electrons into atomic orbitals. Okay. The first part of the orbital is how the average distance from the nucleus, and that's the n level. Okay, that's the principal quantum number. The orientation or the distribution is the angular momentum quantum number. And for every n equal 1, you have s, 1s. For n equal 2, you have an s, 1s, okay, but 3 p's. For n equal 3, you have 1s, 3 p's, and 5 d's, okay, and then you keep on going like that. Okay, now each one of those we said can have 2 electrons in it, one spin up, one spin down. Okay, so you have the principal quantum number, angular momentum quantum number. Now the magnetic quantum number specify an orbital. Now again, we've just sort of hinted around that magnetic quantum number. We never have been very specific on that. Okay, that specifies the atom's quantum state, the basic energy level of the atom. Now, along came Linus Pauly, okay? No, I'm sorry, Wolfgang Pauli, Austrian physicist. There was another Pauli named Linus Pauly. He was, I think, American or maybe from somewhere, but anyway, completely different character. Wolfgang Pauli. He came up with the concept that there's no electron in an atom that has a duplicate set of quantum numbers. Okay, for n equal 1, you have s, 1s, and that 1s has 2 electrons, one's up, one down. That's all you got in your first level. And you have a principal quantum number n equal 1, angular quantum number s, and then either spin up or spin down. That gives you your unique quantum number for those 2 electrons. Okay. In the next level, you have 1n, 1s, but you could have spin up or spin down. Then you have 3 p's, but you could have spin up or spin down. But every electron has one and only one unique quantum number. That's what Pauli's exclusion principle says. The maximum of 2 electrons per orbital, and again we call it spin up and spin down. Sometimes they'll say that, I want to say s, but it's not s because s is used somewhere else, plus 1/2 minus 1/2. However they want to name it, it's spin up and spin down. The chemical properties are determined by that unique electron structure. Okay? That's where the chemistry ties in. It seems like up to now it's been more physics, but that's where the chemistry ties in. Now, this is part of what we're going to be doing in lab today, so it's good we got here. Not a lot of time to spare. This is how you write your electron configurations. The electrons fill available orbitals in order of increasing energies. Okay? The shell capacities, I want to call it the subshell capacity, for S subshell will be 2. For your P subshell, 6. Your D subshell, 10. Your F subshell, 14. Why? Because S has one sublevel, but it can have 2 electrons. P has 3 sublevels, 2 electrons each, so its capacity is 6. D is 5, twice that for 2 electrons per sublevel, and then F 7, twice that is 14. So this is going to show you how strontium electrons fill up. Now strontium, if you go to the periodic table at the back of your book or somewhere in chapter 8, in fact it's coming up in just a few pages, like maybe 1 or 2 pages, 1 page over. There it is. If you look for strontium, that's number 38, meaning 38 protons, meaning for neutral strontium, like we learned last time in lab, 38 electrons. So you have 38 electrons in strontium. Okay, here's how they fill. Now this is a rather strange graph, but this works, and this is the one we're going to come back to do today's lab. So I'm going to try to tell you what happens. Okay, you start up here, and in that first n equal 1, you have one s. The 1 is a principal quantum number. S is your angular momentum quantum number. Okay, though it's not a number. Okay, so you have one s, so you fill up 2 electrons there. When you get to the end of the arrow, you go to the top of the next arrow. Okay, then you fill the 2s, n equal to angular momentum quantum number s, 2 more electrons there. That's all, folks, for now. Then you go to the top of the arrow. You don't go across like this. You go from point of the arrow to top of the arrow. Then you do 2p. Well, you might say, well, that's just 1s, 2s, 2p. Yeah, it is for a while, but it doesn't always do that. So then you fill your 2p electrons. Again, p is 3, so you have 6 electrons there. So you have 2 electrons, 2 electrons, 6 electrons. That adds up to 10 so far. Then you go down here and do your 3s. That's 2 more electrons. That's 12. Then you go up to the top of this arrow. Then you do your 3p. That makes sense. That's 6 more. That would be 18. Then 4s is 2 more. Now notice you do your 4s before you do 3d. The reason is 4s electrons are less energetic than 3d. Remember, the 4s electrons are, even though the energy level, the primary, is 4, these are further away, so their energies are greater. Okay, so what were we? 2, 4, and 6 is 10, 12, and 6 is 18, and 2 is 20. Then you go to 3D, and 3D is another 10. So that gets you up to 30. You're not at 32 yet, or 38 yet. The 4p electrons are, p is 3, 4, and 3 times 2 is 6, so 30 and 2 is 6. When you get to the 5s, you stop. That's where strontium stops. Okay, and that would be the electron configuration of strontium. Exactly like we said, up to 5s and stop. Now, when we get to the periodic table, I'll point out to you what that means. Okay, Now, how do we write that? I think they show it next. Yep, here it is. 1s, and then this 2 means maximum of 2 electrons in s. Remember oh, yuck, go away. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and 5s2. Okay? And that's how they fill up. 1s2, 2s2, 2p6, 3s2, 3p6, then come down and do 4s2 before you go back up and do 3d10. Then 4p6 comes next, and then 5s2 is last. When you get here, you've reached 38. It's 2, 4, 10, 12, 18, 20, 30, 36, 38. Stop there. There's your 38 for strontium. That's as far as you go for strontium. Anything less than 38, you're stopping somewhere up here somewhere. Anything greater than 38, you're moving on down here somewhere else. Okay? Now I think you see why you never exceed F. Because by the time you get here and go to the next level, I'm sorry, I went over, and then the next level, that's the first F you get to, come down here. The next F you get to is here. Okay. If you would have had a G, it would have been out here, but you run out of atoms before you get there. You've reached the maximum that we have, and I'll show you that when we get to the periodic table. Okay. It's not saying there may not be some others out there, but not so far that we've discovered in our universe. Okay, so I think we're fairly safe to say there's not many more, if there are. That's how you write your electron configurations. We'll be coming back to this slide in today's lab. Okay? Now, what does that make a difference? 8.5 goes into, and by the way, there is one thing they call firework configurations, and strontium, the one they mentioned in that last one, happens to burn incredibly brightly in all sorts of beautiful colors. They use it in fireworks. Okay, and I don't know if that smell you got is that, or if it's gunpowder or what. I don't know. So here's your periodic chemical properties. Now this is understood in terms of those electron configurations. The electrons in the outer orbitals determine the chemical properties. Electrons in the outer orbitals determine the chemical properties. Summarized in the periodic table, which I think we'll be showing next. In the periodic table, you have the rows, which are your periods, which refer to your N numbers. Okay, if I could get my pen to show up somewhere here, oh, there you are. These are your N numbers. The rows are N equal 1, N equal 2, N equal 3, N equal 4, N equal 5, N equal 6, and N equal 7. Notice that's as far as we went here. N equals 7. Okay? The columns, okay, represent families or groups, and we'll show this in just a minute. The alkali metals don't act like metals at all. They are very soft, not what we would think of metals, but they indeed act like metals. And those are called the 1A column. We'll show that in just a second. Right next to that are the alkaline earth materials. That's 2A. And by the way, I'm going to come back here and show you those are the things that deal, the outer electrons are these S electrons, depending on which row you're in. The first electron are your alkali alkali metals, and the second one are the alkaline earths. Okay, those two electrons define those columns. Now, they skip way over to the halogens. The halogens are when you're feeling you've got one short of your last P here. That would be a 2p5, a 3p5, a 4p5, 5p5. Those are your halogens. And those all act the same. That's the 7A column. Okay? And then the noble gases, that's when you fill that last electron. 2p6, 3p6, 4p6, 5p6, 6p6, 7p6. When that gets filled, you have a completely full outer shell. They don't want to borrow an electron. They don't want to lose an electron. They are so perfectly happy they don't react with anything. And that's why helium will not explode where hydrogen will. Hydrogen has one electron in its outer shell. Helium has two. Helium's filled. Doesn't react with anything. Neon doesn't react with anything. Argon doesn't react with anything. Xenon doesn't react with anything. None of those noble gases will react with anything. Those are your 8A shells. Now the A group families are the main groups or representative elements. Okay? That doesn't say a lot to me. The B group are what we call the transition elements, or otherwise known as metals. Now these metals don't act very much like these metals at all, except for the fact you have very few exchangeable electrons. You do here and you do here. That's what makes them metals. These are the metals we think of as metals. Iron, nickel, cobalt, gold, platinum, all those are your B groups. Okay. These are your main groups, representative elements that act differently from the metals. Okay, here's one rendition of the periodic table. Now this isn't particularly my favorite, but it will do for now. Remember hydrogen? Only one proton. Here is the mass down here. Here's the number of protons up here. This is not quite the same of what we did in the last lab. This has the atomic number in the upper left, the atomic mass underneath. Okay, they didn't do this in the last lab or earlier in the chapter. So this means in general no neutrons, and we learned that before. But because there is a 0.01, there's some rare isotopes that do have 2 and even one that has 3 neutrons. No, I'm sorry. 1 and 2 neutrons for deuterium and tritium. Helium, I don't remember now, but it seems like it didn't have any isotopes. But if it does, they're very, very rare. Lithium, a little bit less. It had its biggest isotope was the big one, and the lesser one pulled down the atomic number. Beryllium had one above or so. What we did last time builds on this. Here's what we got. One S1, one S2. The outer shell is completely filled. Helium doesn't react with anything. Hydrogen reacts with everything. You never, very seldom have pure hydrogen. It's always reacting with something. Helium, you never have a compound made up of helium. Never, okay? It doesn't react with anything. This is the 1A shell. This is the 8A shell. 8 total electrons everywhere else. In the first row, you've only got 2. Because in n equal 1, you only have S1 and S2, and you're filled. So in row 2, this is n equal 2. Here's your 2S1, 2S2. These are your, except for hydrogen, these are the alkali metals. These are your, that's 1A, 1 or 2A, your alkaline earths. Okay? Beryllium, magnesium, calcium, these are, fill up the second S electron in that thing. And there was your strontium down here at 38, and that's why it stopped at, what was it? 1, 2, 3, 4, 5S2. That's where we stopped. Once it filled that up, it was done. Okay? So then the next one goes over here to 2P1. That's the first one that has a P in it. Okay? And then 2P2, 2P3, 2P4, 2P5, 2P6. Once you filled that shell, you have a noble gas. Neon doesn't react with anything. Now, fluorine reacts with almost everything because it's one electron short of having a filled shell. So if any of these are called your halogens, if any of these can rip off an electron from anything else, it will. For instance, sodium chloride. Sodium's so easy to lose that outer electron, chlorine will gobble it up, then sodium becomes positively charged, chlorine becomes negatively charged. They go together and they're happy campers because they each have filled electrons in their outer shells. Okay? That's your basic chemistry. Okay? So that's your halogens over here. These others, we don't really have names for them. The 3A, 4A, 5A's, and 6A. 7A are the halogens. 8A are the noble gases. 1A is the alkali metals. 2A is alkaline earths. Okay. Then we get down to 3A, 3S1, 3S2, sodium, magnesium. Then you don't do anything here. And here's the reason. Go back here. You see, before you do this one, you go back to the top and do 3P, 4S before you get to 3D. Okay? So that means you skip the D's. These are the D's in here, and do 3S1, 3S2, 3P, 1, 3P2, 3P4, 3P5, 3P6, 3P, 1, 2, 3, 4, 5, 6. Okay, 3P1, 3P2, 3P4, 3P4, 3P5, and 3P6. Then you go and fill 4S1, 4S2 before you start doing your 3Ds. These are your 3Ds down here, even though they're in the fourth row. And that's why before you get to these, you're already in the fourth row. So therefore we put the 3Ds down in the fourth row because they're actually higher energy than 4S. So that's where the D's start here. 3D is right down here. And you have how many? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you go back to your 4P, which you see here. You do the 3Ds before you do your 4Ps. Okay? All right. So there's your 4Ps over here. 6 of those again. See, everything is set up according to those energy levels. Okay? Then you go to 5S1, 5S2, there was strontium. That's where we stopped. Then you go back here and check it out. You go back up to your 4Ds. Okay? From 5S to 4Ds. Okay? And you start filling those up. 5S1, 5S2, 4D1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then you go back to your 5P, which shows right here, from 5S to 4D to 5P. Okay? And you fill those up. 6 of those, 1, 2, 3, 4, 5, 6. Then you go to 6S. 1 and 2, just like before. Well, guess what? Here you go to your 6X. After 5P, you do your 6S. Once you get those two done, then you go up here to 4F. Oh, wait a minute. how are we going to fit that in here? Okay, well, here's what they do. There's, what was that? 6S1, 6S2. Now you go up to 4F. Now, it starts right here. See, 55, 56, but then jumps down here. So this is actually the first of your F. Why they put it here and not down here, I'm not sure. Okay, but that's what they do. And it's called the lengthenide series. How many were these? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then this one really is your next, what is it up to? 5D, I think it is. Let's go back and see. After your 6X, you go to 4F, then your 5D, then your 6P. And sure enough, that's what you're doing here. Now, was that someone trying to get in, or was that my swipe? Okay, we actually may have lost somebody. I don't see anyone waiting to come in. Okay, yep, we're down to 8 students now. Sorry about that. All right, so you see how this works? It's rather bizarre, but it works. Okay, this shows how these things fill, and that's exactly how it does in the periodic table. So then you go through, what was that, 4F, 4F was down here, 5D was up here, and then your 6P was here, these 6 here. And then from this radon, which is a noble gas, you go over to 7S. And 7S is as far down as you went here, 7S, and then you go back to the top and do your 5F. Okay, well, let's see, let's get back there. 7S1, 7S2, then this is called the actinide series, and this is the first of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Actually, 14 is the last of the 5F, and then this picks up whatever LR is, that picks up with your 6D, and it begins right there. And you see, before you get to the end here, you've run out of elements. Now they have a few of these named or numbered, but there are a lot of them UUUs, meaning unknown, unknown, unknown. They don't know if they even exist, or if they do, they're very transitory, meaning they don't last very long. They're so heavy of nuclei, they are radioactive, and they break down in no time. So they're not effectively usable atoms, but maybe in some universe they are. That's as far as we go. That's why we don't go to G's or H's or anything else. We stop there. Okay, that basically is how our periodic table is put together. Oh, here's Daniel. He must have been the one we lost. He's back. So we're back up to, I guess, 9. Let's see, what are we up to? Yeah, 9 students now. So we have lost some others, I think. Let's see, did we ever break double digits? 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 9 was the max we ever had. That's too bad. This is pretty important stuff here. So there's your periodic table. The one that's in your book actually is, to me, a lot prettier table. And we'll be using this one too. I don't know if you can see it. It's in your book, page 220 or 8-16. Now, some of the features that are common here, what this little jagged line, wait, I don't have my pad in front of me. This jagged, well, I'll just do it this way. This jagged line here, this separates the nonmetals from the metals. The metals are basically your B's here. Remember, they did say that. These are called the transition metals. They have very few electrons in the very outer shells, like 1, 2, 3, 4, 5, 6, 7. These 8 here, I don't know if you really count these all in the outer shells, but I did want to point something out to you, especially those of you, yeah, all of you. Remember iron, nickel, and cobalt? Iron, nickel, and cobalt? How were they related? The only 3 naturally occurring magnetic materials in nature. And they're all in one row, that's 1 N number, and they're all in 3 columns that are all called the 8B columns. These down here, we don't notice it in them, only in that one right there, those 3 together. That can't be happenstance. There is a reason for it. I don't know if anyone's ever discovered it, but there is a reason for it. Okay? You see, actually, these F electrons, you should have split the table right here and done another, just like they split here and here. But if you did that, it would be so wide you couldn't fit it on a page. So these here go right after lanthanum and actinide. Okay, so that's what we're doing with that. Okay, I think we beat the periodic table almost to death, not quite, but I can't get it to advance. So let me click on that. Okay, here we go. So let's look. The metals, nonmetals, and semiconductors, they're labeling this. Well, they start off with noble gases. That's a weird place to start. But those are your 8A shell columns. These are filled shells, inert. They do not react with anything. So they would definitely be nonmetals. Even with a high atomic number like radon has, look at that. It has 86 protons. Its atomic mass is around 222. The reason it's in parentheses, it's radioactive, and yet it's still a gas, even though it's that big of an atom. Normally anything anywhere close to that would be a metal. It's not. It's a gas, because it doesn't react with anything, not even its fellow neighbors. It doesn't react with anything. So radon gas is, and you may have heard about that in the past. Okay. Now, when you have 1, 2, and 3 outer electrons, they tend to lose those electrons fairly easily and become positive ions. These are classified as metals, even though some of them are very soft metals. When you have 5, 6, or 7 outer electrons, they tend to rip off other people's other electrons, and they form negative ions. These are typically your nonmetals. So basically, 1, 2, and in some senses 3, these are mostly metals. Boron is not a very strong metal. Okay, these are not very strong metals. They are soft metals, but they are technically metals. 5, 6, and 7, these are your nonmetals, and these tend to rip off electrons. Now, in some senses, they rip them off and form ions, but these, especially in 5 here, tend to what we call share electrons rather than actually becoming ions. These become ions for sure. They rip off an electron and they've got a filled outer shell. They're happy campers. These tend to share more than they rip off, though they could rip off. These mostly share. The ones in the middle here, 4A, these 2 are nonmetals. These 3 act more like, well, I will get to that in a minute. They definitely share electrons. They don't ionize either way, because which way would they go? They're +4 or -4. They share electrons like crazy. And that's why most of your, well, not why, but that you can relate that to most of your organic materials contain carbon. Every organic material contains carbon. Those carbons are sharing electrons. A lot of your inorganic materials, like sands and your minerals and stuff like that, for those who did have Physical Science 1, these are your silicates. Remember them? These are a lot of your rocks and minerals. Are the biggest classification are your silicates. Organic here, inorganic here. That's a gross generalization. Okay. Now, in between the two are what we call semiconductors, in between the metals and the nonmetals. And this one will show it a little bit better. Oh, yuck, it doesn't show it well at all. These show the outer, this is called electron dot notation. Outer electron outer electron, outer electron in all these. Okay. 2 outer electrons in all these, 3 in those, 4 in those, 5, 6, and 7. These are filled shells. 2 up here, that fills the S shell, that's all you got. Then the rest of these are 8. These are almost full, that's why they rip off electrons like crazy. These are, if you lose that electron, then you have a filled shell on your outer shell. You just don't have anything in the what you should have in the outer shell, and the one before that. See, the one before lithium was helium. The one before sodium was neon. So if you lose that electron, they have filled outer shells. But they're not neon, they're sodium ions. Okay? Remember, it's the protons that determine the nature of the element. The electrons, all they do is tell whether they are charged or not. Okay? So, here's the better picture. Now, this is a misnomer. Hydrogen definitely isn't a metal. Okay? It is not a metal. In this case, and you'll see some periodic tables will list hydrogen here and here. And in terms of being a metal, this one belongs over here. Okay, it's 1 electron short of being a filled shell, but it only has 1 electron, so and the filled shell is 2, so really in a sense this belongs over here, but we always put it there. These are your alkali earth metals. The alkali metals. These are the alkaline earth materials, which are sort of like metals, and then everything else in here is a transition metal. Over here, boron is a semiconductor, so it goes with these in here. But under that, aluminum is a metal, gallium is a metal, but these are fairly rare. Aluminum's common, but the others are not. Your semiconductors, remember that jagged line? They are the things that go on either side of that jagged line. Sometime on both sides, some on one. This is on the upper side. This is on the upper side. The others are upper and lower. Okay? Silicon, germanium. I don't think that's arsenic. It may be. SB is antimony, I think it is. Tellurium, something another. Those are your semiconductors. And there's a whole industry out in California, and all over the world based on semiconductors. These are your non-conductors or your non-metals here. These are your metals here, which are usually pretty good conductors. These are your noble gases that don't conduct. They don't do anything but float around by themselves. They don't interact with anything. Okay? So those are really your 4 classes. They only list 3. Metals, most of them. Non-metals, a group of them. Semiconductors, this dividing line between the 2. And then what they left off, the noble gases here. They don't act like metals. They don't act like they're non-metals for sure, but they don't react. These non-metals react like crazy. These non-metals do not. So yeah, they belong with the non-metals. Okay, they're gases. Not many of the others are gases. Hydrogen's a gas, nitrogen's a gas, oxygen's a gas. I think fluorine and chlorine both are gases. And then the rest of these are usually solids. Okay, one weird one down here, where is it? Mercury. It's a liquid. Oh, how weird. But it's a metal for sure. Okay. So those show your three classes: metals, nonmetals, and semiconductors, whereas the noble gases are included as nonmetals. Semiconductors sometimes act more like metals, sometimes act more like nonmetals. Semiconductors. Oh no, don't tell me. Did we finish the chapter? And with 4 minutes to spare. At the top of page 221, you have table 8.4, which is electron structures of the alkali metal family. That's lithium, sodium, potassium, rubidium, cesium, and francium. And you'll know they have one electron, one s electron in their outer shell. That's all. So they tend to lose them. Your electron structures are your noble gases. They are happy campers. 2 in the outer level of helium, that's all it's got. 8 in the outer shell of all the rest of them, down through radon. There's some periodic practice. Identify period and family of the element silicon. Oh, that's easy. Go over to silicon, Si. The period is number 3, row number 3. What was the other thing it asked for? The family was 4A, 4 electrons in the outer shell. Okay, and you can do that with a bunch of them. And then we did 8.6, snuck up on us. The rare earths, those are really interesting. Now these are the rare earths. These are in those these down here. Notice the metals, nonmetals, and semiconductors were all in the upper group. Down here, these are called the rare earths. And they are mostly sort of metal-like, but they have some interesting characteristics. Very valuable, very rare. That's what makes them very valuable. But that's the one nation that probably has more of these than any others is the Republic of Congo, which should make it one of the richest nations on the earth, and it's one of the poorest because it was colonized and brutalized and raped basically by other nations, Belgium being the main one, and they still to this day have never recovered from their basically enslavement to the Belgium. Right now the Chinese are ripping them off like crazy. China is in there like nuts. They bring in their own people, they mine the stuff, they haul it out. They do build roads for them, but the Congolese people don't get any benefit to speak of. Maybe a few jobs here and there, but basically the Chinese are ripping them just like, well, maybe not quite as bad as the Belgians did. Okay, they mention here people behind the science: Dmitry Ivanovich Mendeleev, good Russian name. He developed the first workable periodic table. Now when he did it, there had some gaps in it, but he knew something went in that gap. Up to now we've filled most of those gaps. So he is quite a character, quite a brilliant scientist. Semiconductors are mentioned at the top of 224, and then we'll go from there. You know what? I need to take a break, and it's time to let me take a break. I've got a bladder break coming, got to go. We'll get back shortly, okay? Oh, man. Well, not only did I have a bladder break, my wife had gotten home sometime recently, so we chatted just a little bit, so that's why I was a little late. And I also grabbed a hot banana pepper and ate it. Now my mouth is burning. I mentioned there were semiconductors at the top. Now, did anyone try to get in while I was out? Let me see. I don't see anybody. No. So we got our 9 students. That's all we got today, it looks like. So I'm glad y'all are here. Okay. I mentioned semiconductors, closer look at the top of page 224, or 11 dash, I mean 8-20. In fact, let me close the door because I know it bothers my wife to hear me talk so loud and so much. Okay. I'll get situated one of these days. Okay. Maybe not today, but all right. Then also on page 224 or 8-20 is metals in charge. And they say, is strontium a metal, a nonmetal, or a semiconductor? Obviously, it's way over there. There's strontium right there. It's classified a metal. Probably a soft metal, but it's a metal. Okay. What's the charge on a strontium ion? It's probably going to be a +2 because it has 2 outer electrons. It tends to lose them. So if it's an ion, it'll probably be a +2. Everything in 2A would be a +2. Beryllium, magnesium, calcium, strontium, barium, and radium. Okay. Now I got pepper seeds stuck in my teeth. Okay. So anyway, you can read through those and find that out. Metals lose their outer electrons to acquire a noble gas structure. That's what's happening here. The lithium will lose one, leaving helium. Noble gas structure. It's not helium, it's lithium still, but it's a lithium ion. When sodium loses an electron, its outer shell is just like neon. When potassium loses an electron, its outer shell becomes just like argon. Okay, so electron-wise, it acts like that, and it's happy, except it's now got a charge. These have no charges. Okay, so they float around by themselves. These then will form electrostatic attractions and have a electric bond. What they have a name for it. Bonds. Okay. Now, on the other hand, the number 8s over here, they are one short of being one. If they can rip off one of those electrons, they're happy campers because now they have a completed shell in the outer shell. However, they're now negatively charged, so they're attracted to the positive charged ones, and that's why you get strong compounds like sodium chloride, potassium chloride, all those, they form really strong electrostatic bonds. Okay. The outer orbitals, okay, that's going to be something worth your read, okay, because that's part of what we do in lab is going to answer that. So we did finish the chapter, and like I say, in every chapter, at the end of the chapter, nothing places reading the chapter. So please read the chapter. If you haven't already, read it. If you have already, not a bad idea to at least read it, skim it again. And then at the end, you have a summary. Now, this chapter has a pretty long summary, and no surprise, there was a lot of people involved, a lot of names, a lot of events, a lot of happening there over a relatively short period of time. All this sort of fell into place. They have a summary of equations here. Some of these are pretty fundamental, and some of them are sort of esoteric. So I'll let you look at that. The key terms, maybe a few fewer than some chapters have, but they're all pretty important ones. They're listed alphabetically, but they give the page number in which they're first identified, located, or defined. Then applying the concepts, the very best thing to use to study for your test. There are 49 questions, right about average, maybe one or two more than average. Answers are given, so you can check out and see if you can get them right. Questions for thought, only 12. That's maybe a few fewer than normal. Further analysis, 6 of those. I think that may be one or two more than normal. Parallel exercises, if you have the big book, the Group A exercises have answers in the back. Group B do not. If you have the little book, I think they left those out, but they're still sort of interesting and fun to work on. Okay, so any questions on chapter 8? All right, now what we're going to do now is move to the lab. Now what I'm going to do is leave up here the PowerPoint. Usually I shut it down, but I'm going to leave it here because we're going to be using this like crazy. So let me erase what I've got because we'll probably be drawing again. So let's erase that. Okay, we may use some other figures in the thing, so let's leave that for now. Now let me see, I can't remember if I brought up the lab. I meant to, but I don't see it here. Yeah, there it is. Okay, there's the lab. We don't have the simulation. This is just strictly a book lab. So if you have a book, get your book. Okay, if you happen to have an ebook, I don't know if McGraw-Hill does them, I assume they do, get your ebook. Okay, if you don't have either one, I would say get with somebody remotely, share information, take pictures, whatever. Let's see if we can fill out this lab sheet. Okay, now be sure you put your name. I was going through some tests that I had printed today. I think it was a different class, not this class, and sure enough there was a completed test. Looked like it did pretty well, but no name on the test. So I'm going to have to go back and try to figure out who in the world, when I printed that. This is going to be a pain in the neck. Okay, I may just leave it blank and see who screams the loudest, hey, I know I did that test. Then I'll go and find and say, oh yeah, that's you, but you didn't put your name on it, so I didn't know it was you. Okay, so please put your name. The date I don't care as much about, but it does help. And I'll put the score in. Don't worry about that one. Okay, for the following atoms, identify the number of protons. This sounds familiar, doesn't it? Number of neutrons and the number of electrons. Now I've written them the same way we wrote them last time. Okay, so you should know how to do this based on the last lab. If any of you weren't here for the last lab, we'll go through that. Okay, so that's the first columns here. I picked out 4 elements: carbon, magnesium, iron, and gold. Okay, so what we'll do is identify the number of protons, neutrons, and electrons. Let's do that first. That's pretty easy. How many protons are in carbon? Anyone want to offer a guess? 6. That's that number at the bottom. How about magnesium?
12.
All right. Iron?
26.
26. Okay. And gold?
79.
79. Boy, we got some. Down here we're going to do some drawing, aren't we? Okay. Now, how many neutrons are in carbon? How do we determine that? The difference. And how many would that be? 6. Magnesium? 12. Iron?
26.
Well, okay, let me see. I can't read my thing there. To me, that looks like 56 and 26. Am I reading it right? Okay, what's the difference in 56 and 26? 30. Okay, let me just make sure I did it right. Yep. Okay. All right. And how about gold?
118.
118. Perfect. Okay. How many electrons? Now what we're assuming here is neutral carbon, magnesium, iron, and gold, not ionic, neutral. What would be carbon? What would be carbon? Okay, does someone have a radio on in the background?
My child's watching television.
The television, okay. If Okay, I appreciate it. I want you to be able to participate. You'll need your microphone for that. Now, if somebody else in the house is watching it and you can't help it, that's okay. It's not that distracting, but it just seemed like something. Okay. All right. Did you ever figure out how many electrons for carbon? Neutral carbon?
Is it 12?
Not 12. 12 is the atomic mass. That's the sum of neutrons and protons. For it to be neutral carbon, neutrons have no charge at all. So you'd have to have the same number of electrons as protons. Okay, so that would be 6. Magnesium,
12.
iron,
26.
got it, and gold,
79.
79, got it. Okay, that was easy, wasn't it? We remembered that from last time. Here's the part that's going to take some effort. What's the electron configuration of carbon? Now remember, it has 6 electrons. So we go to our table. Okay, if I can get it to come up. Remember that handy dandy table we have? This one right here. Okay, where is it? Go resume the slideshow. Here it is. Now, unfortunately, that thing's right in the middle. We start until we get to 12. 1s is how many? 2. 2s is how many?
2.
That gives us 4. 2p is how many?
6.
6. That gives us
10.
10. And 3s is?
2. That gives us 12.
That gives us 12. Okay, which one were we doing?
Carbon.
Okay. Oh, wait, no, we're only going to 6. We're not going to 12. 12 is the mass. We're only going to 6. Sorry about that.
Also, actually, we did the next one.
Right, yeah, we did. Okay, I thought that's why I paused there. I said, that's magnesium. Okay, let's start again. 1s gives us how many?
2.
2. 2s gives us
2.
how many? Total of 4.
4.
And then we only need 2 more. So it's 2p2. 2 here, 2 there, 2 there. There's our 6. So we would write 1s2, 2s2, 2p2, stop. That's carbon. Okay? Now let's go back to, that's not what I wanted to do. Oh, I know what I want to do. I want to go to the periodic table and show it. 1s2 right there, 2s2 right there, 2p1, 2p2. There we are, right there at carbon. So that one was fairly easy, right? Now I know I can't get all these things on the screen at the same time, but that's what you do for the electron configuration of carbon. So you can write sort of big on carbon, you got plenty of room. By the time you get up to gold, you're going to have to write a little bit smaller. So this is 1s2, 2s2, 2p2, that adds to 6, right? And as Valerie or somebody pointed out, we did magnesium before, we're going up to 12 electrons. See, the 12 is an electron here. Now, I hope that's what you got there. So let's go and see how we get up to 12. We did it before. We'll do it again. Okay. Resume slideshow. Okay. Oops, that's not the right one. Go back to, okay, here we go. We start here, 1s, how many is that?
2.
2 s's, 2. We're up.
Sorry, 4.
Yeah.
That makes 4.
Up to 4. 2p is how many?
6. So that
6. 10. And 3s is
2, and that makes
12. And there's where we stop. That is magnesium. 1s1, 1s2, 2s2, 2p6, 3s2. Okay, go back here. Okay. Oh wait, no, here. Periodic table. 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, and 6. 3s1, 3s2. That's where we are. Stop right there. Okay, there's magnesium. All right. Any questions on this? Is it going too fast? Is it okay?
So when you're going to the periodic table, we can't, well, I can't see it. I don't know about anybody else because there's a.
Oh yeah, that bar there. I'm sorry, I wish I could do something with that, but I can't. But if you got your book, that's why I said it's really important to have the book. You can see it in the book. Now what I can do on the periodic table, let's go back there now that you mentioned that. Okay. What I can do is, there it is without the bar. Okay. I don't know what happened to the bar, but there it is. It's not coming back. Yay! Okay. Down here it's there, but it's not there. So look, we can do it now. 1s1, 2, 2s1, 2, 2p, 2p, 1, 2, 3, 4, 5, and 6, 3s, 1, and 2. Stop there. There's magnesium. See? Now these are backwards, okay? I don't know why they do it. The 12, according to the way we've been doing it, the 12 would be down here, the 24 up there. Okay. But on the periodic table, they put it the other way. Okay. Anyone else need to slow down or rehash? Okay. Our next one is iron. How many electrons? 26. So we're going to go up to 26. Let's go back to our chart, which is on the slideshow, and go back to resume the slideshow and go back to the chart. Okay, we're going to 26. So let's count. 1s is how many? 2. 2s's? 4. 2p is?
10.
Yeah, 6 is 10. 3s's?
12.
12. 3p is?
18.
18. 4s's?
20.
20. 3d is how many?
6.
Okay, now d would go up to
10.
10, but we don't need them. We only need, you're right, we only need 6 because we're at 20 here. We only need 6 of these. So that will stop at 3d6, not 3d10 like you see down here. 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, wait, yeah, 4s2, and 3d6, because this gets us up to 20. We only need 6 of those 10. So let's go and see where that lands us. Oops. On the periodic table. Here's 1s1 and 2, 2, 1 and 2, 2, 3, p, 1, 2, 3, 4, 5, 6, 3s2, 1 and 2, 3d, 1, 2, 3, 4, 5, 6, no, p, 1, 2, 3, 4, 5, 6, 4, s1 and s2, and then 3d, 1, 2, 3, 4, 5, 6. There we are. See the periodic table? You can do it that way too. Does that make sense? And there's your 26 here, your 56 there, rounded. Okay? All right, that took a while, but it was doable. But this next one, gold. It's going to be worth it, but it's going to take some work, isn't it? How many electrons? 79. Oh man, this is going to be hard to keep up with, but let's see if we can do it. Okay? I'm awfully slow at this. Sorry about that. Okay. Go back to 1s is 2. In fact, if you wanted to, let's just do this. 2, 4, 10, 12, 18, 20. And let's just do 10 more, 30. That gets us down to there. Okay? Right there is where we filled that shell, 30. We're going to what? 79, was it? What was gold? Okay, 79. So we're at 30 right here. Then this will be 36, 38. That was strontium. So we can stop there at 38. So let's pick up from here. Next thing we do is go to 4D. How many were in D? 10 more. So that gets us up to 48. How many were in P? 5P, 6. So 48 and 6 are 54. Is that right? Believe so. Okay. My math is lousy. 6S is how many? All right. Okay. Let me see if this will help. I don't know if it will or not. Let's go back. Where did it go? Oh, Rodrigo's coming back in. I already have him present. So Rodrigo, when you get here, we've already started the lab. So if you get your lab, it's under the week 7 instructional materials. The lab is there. If you can print it off, fine. If not, just start filling it in. Get with a partner. I think you may have one, and fill in the blanks. So what we're going to do, I'm going to cheat a little bit here, and I'm going to write in some numbers, and this will make it easier to keep up with. If I can get the pen to show up. Where are you, pen? Okay, here we have it. So this was a 2, a 2. Tell me what goes here. 6. Yeah. 2. I can't get the pen to write. 2, 6. I wrote 6 here, but it didn't write. What was D?
10.
10. What was S?
2.
What was P?
I'm thinking that's my computer and that's yours. 6.
6. D?
10.
10. Okay. Oh wait, I'm not going right. This was 2. Okay. Now, P was what?
6.
6. S was what?
2.
2. Goodness gracious, this thing keeps messing up. All right. Now, let's just stop here and start counting. Okay? Yeah. So this is, goodness, where is the pen? Okay. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, right? 56, this is another 10, 66.
No, F is 14, isn't it?
You're right, you're right, you're right. I'm sorry, 14. Yeah, absolutely. I was looking at the wrong one. Okay, I got lost. Okay, 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, and 56, and 14. Well, that comes up a nice 70, right? We got to get to 79. This is another 6, right?
No, that's 10.
That's 10, I'm sorry. So we don't need all those. Okay, we stop and only do 9 of those. So this is going to stop and be 9. So basically, we'd have everything we've got here, plus add to it, stop right here, pick up here, and do a 4, D, 10, a 5, P, 6, a 6, S, 2, and then start here, go up to the top here, and do a 4, F, 14, and then 5, D, 9. I think that's where we end, isn't it? Wasn't it 79?
Yes, 79.
Okay.
Yes, but okay, my question is on the electron configuration.
Right.
When we're actually writing it down, it needs to be in this order?
Yes. Just like you see strontium here, you need to do it in that order. You go
So 5D was the last one?
5D9 is the last one. Yeah.
Right, 5D9. Okay, don't take this down yet, please.
Okay.
Let me get it.
All right.
Okay, that's 1S2, 2S2, 2P6, 3S2, 3P2.
No, 3P6.
Oh, that's 3P6. Okay.
Yeah.
3D10.
Wait. Okay, you're not going in the right order. Okay, remember you go down the arrows. Okay. You start here, go up here, here,
After 3P6, let's see where I'm at.
then 4S2.
No, 4S2.
Right.
S2.
And then after 4S2, you go up to the 3D10. Then,
4P6.
right, then
5S2.
Then you go up to,
4D10.
right, then,
5P6.
got it?
6S2.
Yeah, and then you go to,
4F14.
got it. And then,
5D9.
yep, that gets us to 79. Excellent. Everybody got it?
See, I cheated a little bit.
Oh, okay.
I started with the one at the bottom of our PowerPoint right here, which was 38.
Right, yeah,
It kind of helped me, and I started it from there.
yes. That's kind of what I did too. Okay. All right. Let's go over a couple slides and see if that makes sense. There's 1S, 1 and 2, 2S, 1 and 2, 2P, 1, 2, 3, 4, 5, 6, 3S, 1 and 2, 3P, 1, 2, 3, 4, 5, 6, 4S, 2, and then 3D, 10, then 4P, 1 through 6, then 5S, 1 and 2, 4 D, 10, okay, up to here, and then 5P, 6, Okay, 6s2, and then your
4L14.
yeah, 4L14. Here we go. Oh wait, that's these down here. Okay, it really starts with lanthanum and goes to your rubidium or whatever, and then that LU starts this one right here, and that would be your 5D6 again. No, 5P6, and then 7, right? 7S2, and then we go to your 5F, and you only do 1, 2, 3. Oh wait, I'm sorry. Yeah, that. Okay. No, this we already did the 4F here. 4F 14. That's those, and then we start on the 5D 1, or actually here is at 1, 2, 3, 4, 5, 6, 7, 8, 9. There we are. That's where we go. Okay, good deal. Those electron configurations are plenty to think about, and it's so nice to have that kind of a table. Helps you keep them straight. All right. Any questions before we leave this and go back to the sheet or pillowcase or whatever? Okay.
Can we go over iron one more time?
Okay, let's go back to iron. On the okay.
I'm ending up with 30, and don't I supposed to end up with 26?
26, you're absolutely right. Okay, so let's go back to iron, and it's this one and that one, and here we go. Now I'm going to erase what we did because this is gold and I don't want to confuse you. I can't get my pen to. Why did it do that? Come on, pen. Okay. Now I've got to go back to this. Nope, wrong way. That. No, okay. There we go. Okay. Oh, let me get strontium in there. Okay. We got 1s2. If I can get my pen to show, there it is. 1s2. Remember, that's a 2. Then you go from bottom here to the top there. 2s2. That's 4. Then we go to bottom to top. 2p6. That's 10. 3s2. That's 12. And what are we going to? 26, was it? So we have to go to the top up here, and there's another 3p6. So this was, I got lost. That was 2, 4, 10, 12, 18, and 2 more are 20. And then you go up here, and this was 3D. We only need 6. So you stop right there and do a 6. You don't do a 10 because we didn't use all 10. We stopped at 6.
Interesting. Why am I getting 30?
Because you use the 10 down here. Don't use those.
Okay, I got you. Yes, sir.
Yeah.
I got you. Thank you.
Right. You only fill 6 of them. And here's why. See, with strontium, you went all the way, got all these done, all those done, and then you got the strontium. Well, with iron, you don't go to the end here. You just use 1, 2, 3, 4, 5, 6 of those and stop there. So it ends at 3D6. Okay. Now, okay. Any others before we leave? And we can come back anytime you want to the electron structures. Any more electron structure questions? Okay, to go back, let's go back to our sheet then. Here it is. All right, now we need to answer the question, what period are each of these in? Now that, to me, the best place to go would be the periodic table. That gives the periods, right? So let's go back to our share PowerPoints and go back to the resume the slideshow. And there we are, right there. Okay, what was the first one we had? Oh yes, what's the question? Why what? Because they got a lot of electrons. No, you just are very busy. Okay, you're absolutely right though. That would, but you see, after a while, some of these got so many in them that, you know, like 10s and 14s, you really don't need that many more to do. But you know, yeah, they're long enough. I'll agree with you. But I wanted you to do a few short ones to get your feet wet, and then at least one long one. That's why gold was in there. Okay. Now, the first one was carbon. Which period is carbon in? Period are your rows. It's in 2. You're absolutely right. If I could get my pen to show up, oh, there it is. There's row 1. Here's row 2, and that's where carbon lives. If I could get the pen to show up, right there, in row 2. Where does magnesium live?
3.
Row 3. There it is, right there. So it's in row 3. Its N would be 3. Okay, N here is 2, N here is 3. What's the next one? Iron. What?
4.
That would be 4. Even though the electron that you're there is your 3D something another, it's still in period 4. And then what was gold? 6, exactly. Jumped way down to here. I had to get a long one for Jacob. He wanted a long one. Okay. Okay. All right. So that takes care of that. Was relatively easy. Okay. What's the next question?
The family.
The family. Now the family are the columns. Okay. So let's look and see if we can get the families. And we'll go to slideshow. The columns. And the first one we had was carbon. In which column does carbon live? You see it?
What is that? IV?
Yeah, IV, that's Roman numeral 4A. Okay, you think it's Iva Jane. That was my grandmother. No, okay. No, it's 4A, Roman numeral 4. So usually when I write that, I write it so you don't make that mistake. If I can get the pen to show up here, I would write it as IV with a bar over and under that A, and maybe put a little space between it. It's a 4A. What's magnesium? Okay, that's 2A. And I would write the Roman numeral 2 with bars over it, 2A. That makes it easier to read. I don't like IIA. That is Roman numeral 2. Okay. What is iron? What family?
Is that 8B?
That's 8B. So I would write that, as I guess you would guess by now, if I could get my pen to show up. Here we go. VIII, that's 8, 5, 6, 7, 8, B. And what would gold be?
1B.
1B. And usually I put the I with bars over it, which still looks like an I, 1B. Perfect. Those are the families. Okay. Now, what's the next question? Is it a metal, non-metal, or semiconductor? Okay. We're looking at these 4. carbon, magnesium, iron, and gold. Looking to see if it's a metal, non-metal, or semiconductor. Okay, so let's go back to our PowerPoint. If you got your book, use your book. Okay, why can't I? There it is. Okay, I couldn't find my. Okay, now, okay, let's go over a slide or two. That one. Okay, carbon was up here in which category? Non-metal. Magnesium was over here, believe it or not, in which category?
Metal.
Metal. Iron was over here in, not too surprising,
Metal.
metal, and gold was over here, also not too surprising, in metal. Okay. Those were easy, weren't they? Okay. Everybody got it? Don't let me go too fast. Any questions?
Say it again.
Say that again.
Yes.
What? I couldn't hear.
You said they were the last two were metal, iron, and
Actually, the last three were metal. Magnesium, iron, and gold are all in the blue metals. Now, magnesium is an awfully soft metal, but it's still classified a metal. Okay? Carbon, though, is classified a non-metal. That's the green. Okay? Any others? I'll get carried away sometimes, so don't let me get carried away. This is fun stuff, and it's old hat to me, but it's not to you. So what's the next question? The number of outer orbital electrons. Now that's kind of hard to say for sure, but the best thing to go by, in my mind, is, and it may not be completely true, but it's going to be mostly true. And here we have that thing here again. But the best thing to go by would be, you see, these don't show the transition metals, so this wouldn't be. It has some of them in there, but not most of them. What I would go by was, why won't this advance? There we go. And now this thing is in the way. I'm going to erase as much as I can and hope this will fade out one of these days. Well, the first one, carbon. This is exactly what you look for. What was this number up here?
4A.
4. Yeah, the number only. 4. 4 outer electrons. Okay. Magnesium. What was its number?
2.
2. Got it. Iron is hard to see because iron is right here, and yeah, now it's 8. Now whether there's really 8 or not, I'm not sure, but let's just put it down because that is its thing. The B's don't always follow where you expect, but that's the best we got, so put 8. And you don't have to put Roman numeral 8, you can write the number 8. And gold would be what? 1. You got it. Okay. And just of interest here too, to me anyway, gold and silver are both very precious metals. They don't react with very much of anything. They're not as non-reactive as the noble gases, but that's what makes them precious metals. Now copper is a pretty important metal too, but it's not nearly as rare as gold and silver. Now the other one that usually you put in that category would be platinum, and I'm trying to remember where platinum is here. There it is, it's right next to gold. So these three here are usually considered very precious metals. They don't really react with very much. This is the end of 8 and this is the beginning of 1. So I don't know, I can't explain that, but they are pretty thick. Now if you think, mercury doesn't seem to react with a lot either. However, it will react with some things. You sure don't want to digest any mercury or absorb any mercury because it can really screw up your immune system. Same thing with lead. So the heavy metals down here, you don't want to mess with them, and you don't want them messing with you. Just as a point of fact. Okay. It seems like to me we're pretty close to being through with this lab, aren't we? Are there any questions on it? Except Jacob wanted a bigger molecule. I think he said he wanted uranium, didn't he? You can do that out here in the margin if you want to, okay? Oh, you didn't, okay.
Did you say that we can take a picture of it?
Take a picture of what? Of your lab? Oh, yeah. And send me the picture? Yeah, that's fine. Okay. You can just write down the answers. I'll have the questions and I can follow them. But if you do something like that, be sure you have your name on it, okay? Because that's the only way. If I do a lot of printing, sometimes I don't notice whether names are there or not. And if I neglect to see that, then a few hours later, I don't know who in the world that was, okay? So be sure you put your name on it.
And this is the last lab?
Unfortunately, I know you said that so sadly, didn't you? That's it, folks, okay? So let's talk about what we're going to do on Tuesday then. And it may not be your last lab, but what Tuesday is, now that we finished the chapter, we finished the labs, here's what I'm going to do. Sometime tonight or in the morning, I don't know if I have enough energy tonight to do it or not, I will post your Chapter 8 test. And that way you don't have to worry about Chapter 8 test during finals week. So I'll post it either tonight or sometime in the morning. Okay? I'll post your Chapter 8 test. I'll post it both in Blackboard Message. I always do that. And if I can post it under week 7 or 8, I don't know, wherever I can find a place, it'll definitely be in Blackboard Message. Okay, so it'll be there, and you can start working on that this weekend. When you finish it, turn it in. Now, the reason I'm doing this test is going to take maybe a bit more effort than some of the others did. You're going to have to use your books. You're going to have to use your notes and things like this, because this chapter to me was just packed jam full of stuff. I mean, just packed full of it. So it was hard to get simple enough questions. So I just used what was in the test bank, but I think you can do it. Okay, so I would definitely not postpone this until finals week. I'd do it this weekend if possible. Okay, now, so what in the world do we do on Tuesday? Tuesday is going to wind up being pretty much a makeup day. Okay, and what I mean by that, if you have any questions from any lab, from any test that's been puzzling you, you've been stuck on, bring that to the class on Tuesday. And if you're behind a lab or something like that and you need to run through it, I may not be able to do everything there, but I will point you to the YouTube video that has it in it. And then you can follow there. And then if you have questions, I'll still be here. So basically Tuesday, since we did finish the chapter today, there will be no new material on Tuesday. It'll all be review. Okay? And then whenever as many people as are here are through with whatever they're going to do, then I'll post the final exam as soon as everybody else leaves the class. Okay? And that way you can get started earlier on your final. So
And you said the final is due on before Thursday.
No, technically it's due on Thursday. Now for Amia and any of the others of you that may be graduating this term, not in the spring, but this term, you need to get the final in to me by Wednesday if you can, so I can get it graded, your grades averaged, and get the grades out there. It's not going to matter a lot, but they do sort of want to have that happen, uh, because you'll still be going through the ceremony whether you, well, I think all of you are going to pass the course. I sure hope so anyway. You've been doing really well so far. A few of you I haven't seen too many grades yet, so I'm going to be grading like crazy between now and then. So hopefully by then you can ask me, well, what did I do on this? What did I do on that? I won't guarantee you I have all the answers, but I'll have as many as I can by then. Okay? Now, I do know that Monday morning I've got to go in for blood work again, so there goes part of my office hours Monday morning. But except for that, I don't have any other doctor's appointments or other things like that. So I hope to be able to get a lot of work done between now and then. Tomorrow, hopefully I got 4 hours solid to do, maybe some in the afternoon as well. And then as long as my wife doesn't have too many honeydews to do on Saturday, maybe I can get a lot of things done Saturday and Sunday too. I've got Sunday school class on Sunday, and other than that, hopefully we'll have some time to get, oh wait, no, I'm sorry, wait a minute. We've got to go up to the lake because of the freezing weather we had this week. We've got to go up and make sure that none of my wife's parents had a place up on Smith Lake, and since they're in the 80s, we're taking care of it for them. So we got to go up and make sure no pipes burst. So I'll be still grading papers up there, but I won't be able to put things on Blackboard. So I'm sorry. So Friday afternoon, well, actually we may not go until Saturday afternoon. So I'll have Friday and Saturday morning to work on. No, Saturday morning we'll be getting ready, packing and stuff, and we got to go to the market. So I don't have as free a weekend as I thought I did. I remembered we have to go up there and make sure there's no burst pipes. So we'll be coming back sort of early on Sunday, so hopefully we'll be able to get some grading done on Sunday afternoon too. So Monday morning I've got an appointment in the lab, so I've got to get that done, but Monday afternoon I've got more time. But I've got so much late stuff has come in that right now I'm still printing. I'm not even grading. So I hope to get the printing caught up soon so I can get to grading. So sorry about the delay. Part of that was because of the anemia, because I just had no energy for a month. I mean a solid month. And then we were having some problems with my computer talking to the printer, so I wasn't able to print a lot of the time. And we had some internet problems too, but those were minor. But I'm going to try to get caught up. So far, knock on wood, the printer and computer have been recently talking pretty nicely to each other, so they've been printing out pretty well, I hope. Any questions?
I just wanted to say, if you guys look me up on Messenger, if you are struggling with any of the labs, or you behind, or just have a few questions or whatever, if you hit me up on Messenger, we can get it done. So you don't have to just not turn it in if you're struggling with it.
Thank you. That's what labs are about. Teamwork. Okay. Thank you for doing that. And I'll be here Tuesday, so I'll answer any other questions on Tuesday. Okay, anything else, folks? Any questions on this lab? Was I going too fast? Did he catch up? I know Rodrigo was out for part of it. Yeah.
Yeah, I didn't get the answers of the very last ones for carbon and magnesium.
Okay, which was that? You mean number of outer orbital electrons?
Yes, sir.
Okay, let's go back to our PowerPoint. And back to resume the slide. Okay, and here's what we were using. You said magnesium, carbon and magnesium, is that what you said?
Yes.
Okay, carbon, outer electrons look at the number of the family. And that's a Roman numeral what? 4. So that would be how many electrons in the carbon's outer shell. You don't have to write Roman numerals, write the number 4. Okay, magnesium, what would that be? 2, exactly. Did you get iron?
Yes, it was
8. And gold was 1. You got it. Okay, good deal. Any others? Good questions. Any others? All right. Going once, going twice. Okay, unless there's any objection, I'm going to stop sharing. I'm sick and tired of sharing. Okay, and now we're at the point of ending it for everybody. So let me review. Please do your student course evaluations. They're also called surveys. Look for that email. If you can't find the email, has any one of you done the surveys yet?
I have.
You have. Okay, Valerie will help walk you through how to do those. Do you mind?
I mean, I just went straight to my email and I didn't
Right.
put in the password or anything.
Okay, and what email did you use? Your A number email?
Yes, my A email.
That, I think, is the key here. If you go to your A number email, and if you don't know it, go to the home page of the Lawson State web page, home page, and in that light blue row, that's the third row down, there's 2 dark blue rows separated by the Lawson icon. Then right below that second row is a light blue row, and right near the middle is one that says something like new emails or something to do with email. Click on that, and that tells you how to get your new email and how to log in and what your password, all that kind of stuff is. So once you got that, then go to that and find the email that contain your survey information. Then please do the surveys. Okay? Good deal. And do them for first mini term, second mini term, full term classes. Do them all. Okay.
Oh, it breaks them down for you.
Excellent.
I
Excellent.
had like a class for mini 1, a class for mini 2, which is this one, and I had one for the full term.
Yeah. Okay. And then also, okay, be sure you get your research papers in by Tuesday. Earlier is better. Tuesday is when you get full credit. After Tuesday, you start losing points. Okay, so get them in by Tuesday if possible. And get all that you can of your labs and your tests in, and that's mostly what Tuesday is for you to, if you are stuck on some of those labs or tests, bring those questions on Tuesday, and we'll I'll show you how to get to them or whatever, and then we'll go from there. If you want to know, I can't say I'll have everything graded then, but hopefully I'll have made great progress or some progress on grading, so you can ask questions on that too. Not, I'll put it this way. If you have questions that are not out there, then I'll go on and put what I can. Like if I haven't found a test and you say, yeah, I emailed it to you, blah, 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 then I'll go out, find the email, print it out, and if you've got time while you're there in lab, or in class, I will grade it for you, and then I'll post your grade on Blackboard and you can see it. I won't call out your grade, but I'll post it for you on the spot if you have any questions like that. I'll do that as much as I can for as many as I can until we run out of time. Okay?
So are we, I can't say we, will you drop our lowest test score and our lowest
Lab score.
lab score?
Absolutely. So what I'll do, like you just said it, the research paper cannot be dropped. The final exam cannot be dropped. Your lowest lab score can be if that helps your average, and your lowest test score can be if that helps your average. Now we will have had 13 labs, so I'll count the highest 12, and we will have had 6 tests. I'll count the highest 5. Okay? Now, if you got a score that's dropping it is going to hurt your average, I won't drop it. Okay? Like if you have, uh, super good scores on your test, but either the final or the paper grade was not quite so good, and the test is going to pull up your paper grade, I'll leave it in there. Okay? So I only drop it if it helps your average. I only do what helps you average, not what hurts it. Okay? Surely. Any other questions? Great questions, by the way. Okay. Good deal. That's been fun. And have a great weekend. And folks, please be safe. The COVID is just going crazy right now because people aren't wearing masks. They're not social distancing. They're getting together. I'll just give an example from our family. My wife's brother's youngest son has been dating this girl, and we knew it was getting pretty serious. It's serious enough so they had the meeting of the families. Her family lived in New Orleans. Karen's brother's family lives in Alexandria, Virginia. So Josh and Meredith were meeting in New Orleans. They're both working in Houston now, so everybody gathered in New Orleans. They had a good time. They had a nice meal together at their house, and the next day Josh started feeling bad, got tested. He had COVID, and since then everyone tested positive. Her parents, his parents, and she did. So all 6 came down because they were very cavalier about it. They all have it now. So far, as I've heard, none of them are very severe, thank goodness. But I know that, okay, this was before Thanksgiving, by the way. It's the weekend before Thanksgiving. Sheila, Keith's wife, had planned to have the entire family there for Thanksgiving. Again, being very cavalier. Fortunately, they found out Josh was positive before Thanksgiving, so his sister, who has 3 little boys, didn't come. Her husband's a dentist. If he'd have come and gotten it, he would have been out of work for probably 2-3 weeks. Okay, the parents, not Karen's parents, but the wife's parents, probably would have come. Mr. Kaysen has pretty far advanced prostate cancer. He probably wouldn't have survived. Okay, the mother probably wouldn't have survived. They were so fortunate that they found out about it before Thanksgiving. But of course, Sheila had a whole, probably a couple refrigerators full of food ready to be cooked that she couldn't. She had no one to feed it to. So, folks, it's no happenstance. It's happening all over the place. Be careful. Don't take risk. I want to see you next week. I want you to finish. I want you to graduate. I want your family to be healthy. I have one of my adjunct math instructors. Their son came home from college. He brought it with him. The whole family has it now. The boys didn't affect them too much, but the parents are really suffering. They're not super bad. It's awful coughs, and they're able to cook and move around, but they're just feeling miserable. And Karen's brother and his wife, they said, they were acting like, hey, this isn't too bad, until the weekend they completely ran out of energy. I bet you they were feeling a lot like I did when I had critical anemia. Okay, and I tell you, that's not a good feeling. They had no energy at all. So it's nothing to play with. Be careful, be safe. Okay, we'll get over this once the vaccine hits and stuff like this, but it's going to take a while. Don't risk hurting somebody else or your own health. Be careful. lay low for a while. For instance, at Christmas, we're not going to Georgia. We may not even go up to Huntsville. Karen's folks are in Huntsville. My family's in Georgia. We're definitely not going to Georgia. They're completely out of control over there. Huntsville, we may not go up there either. We may have a very quiet, uneventful Christmas, okay? But that's better than catching COVID, okay? So be careful, people, okay? That's my paid political announcement, okay? It's not political. It's common sense. All right, any other questions, thoughts, parting shots? Okay, if nothing else, I'm going to end the meeting ripping you off of 45, 50 minutes of your tuition dollars. Here I go again. Sorry about that.
Have a good weekend, everybody.
You do too. Thank you much.
Later, dudes.
All righty. Bye-bye.